¿Lo que pasa? Ellos, ¿no quieres que ellos te escuchen tampoco?
There are 10 minutes before our conference starts. All right. Hello, everyone. Good morning, good afternoon, and good evening, depending where you are in the world. I'm happy to start this opening remarks. My name is Yuanqi Du. I'm from Cornell. This is our second year of Learning on Graphs conference. So before we start, there are some key information that you may be interested in look at. First of all, we are all communicating through a Slack channel. It would be great if you could join, and all our schedules are on our website, and everything will be, the whole program of the conference will be live streamed on Zoom and also on YouTube. And we also have poster sessions and the social hours using GatherTown. Please do not hesitate to let us know, either via Slack messages or emails. First of all, about our mission and why we started Log. So it started with a simple idea where we want to support this ever-growing community of graph and geometric machine learning. We want to share the latest advances. We want to build a community where it's truly accessible to everyone, free to attend, virtual and recorded, and supported by many local meetups and local communities. In particular, we always emphasize the importance of review quality, and that's also another benefit of a dedicated community, where we provide monetary rewards supported by the generous sponsors and accountability to incentive review quality. And next, I'm very happy to introduce our two program chairs, Professor Soldevilla from Johns Hopkins and Dr. Ben Chaplin from Charm Therapeutics. Next, Professor Soldevilla will introduce you about our programs and some statistics about the programs.
Hi, welcome everyone. So this year we had a very large participation. We had over 700 registered participants. We have 192 paper submissions, 52 poster presentations, 12 oral presentations, 328 reviewers, 33 area chairs, 10 reviewer awards, 3 area chair awards, and 13 local meetups. In our submissions, we had 70 abstracts and 122 submissions, full submissions, of which we selected 6 oral presentations from each one. There's going to be 26 posters that correspond to abstract submissions and 32 posters that correspond to full paper submissions. And the acceptance rate was 45% for abstracts and 31% for full papers. So this year, we had a few new topics from respect to last year. We had some topics in algorithmic reasoning and also in diffusion models. And we have authors from 22 countries and regions, including United States, Europe, China, Japan, South Korea, Australia, Turkey. And each paper had, on average, 3.5 authors. And the most collaborative paper had 10 authors, and 12 papers had 1 single author. 92% of the submissions received at least 3 reviews. And on average, we had that each review had 400 words. Just some statistics.
All right, and then about our program, we have a 4-day program where we start with opening remarks today, followed by a sponsored keynote from Dr. Kristof Schütt, and then we have 4 other keynotes from Professor Jure Leskovec, Andreas Lucas, and Stephanie Jingelka, and Professor Kyle Kramer. And we also have 2 poster sessions featuring all the 60 posters we've just mentioned, and 4 oral sessions spanning 4 days, covering many topics related to graph and geometric machine learning. And we also have two tutorials, one about scalable GNN training using high performance computing and supercomputing, and the other one about GNNs for recommendations, reproducibility, and graph topology. At the same time, we're joined by 13 local meetups, which 10 of them will be hosted around the same time as the conference, and 3 of them will be slightly over the next year. And we could also see in the room there's a local meetup from Madrid and Trento, Italy. Yeah, and then we are always thankful for our advisory board and new advisors, especially Professor Wei Wang from UCLA, who supported us this year, and all the previous advisors for their continuous support. Regarding organizing committee, this is a quite young conference, and most of the committee members are junior and the students and postdocs, early career researchers, and we want to highlight several new organizers this year. Alex from Paris, and Mathieu from UCL, and Dominic from University of Montreal and Valence, and Xinyu from University of Montreal, Mila. And also, we cannot make the monetary reward happen and everything about this conference happen without our generous sponsors. Especially the past year has been a tough year for industry, but we are excited to share that we have raised a decent amount of fund from our previous sponsors and new sponsors, especially Pfizer and Genotech, for their continuous sponsorship as gold sponsors. And also we have the silver sponsor, Knowing Research, and the bronze sponsors we have continuous from Kumo, and new sponsor Charm Therapeutics, and new sponsor Genesis Therapeutics, previous sponsor Neo4j, and Alice Munich unit. And then I'm going to pass to Dr. Ben Chamberlain to introduce our awards.
Thanks very much. It's my great pleasure to announce the best paper at this year's LOG conference, which is representing edge flows on graphs via sparse cell complexes. This paper achieved incredible scores, 8, 8, 10, 10 from 4 extremely engaged reviewers. And the AC's meta review stated simply, this is a great contribution to the conference. And this work is sort of bringing together ideas from topological data analysis and spectral graph theory, and also includes a very, very nice proof of MP hardness, which a lot of the reviewers remarked on. So congratulations to Joseph and Michael for a really outstanding piece of work. At LOG, we also recognize area chairs, and 3 area chairs that we felt really went above and beyond what is normally required or asked of an area chair. So in all of these cases, essentially these guys acted almost as reviewers themselves. In fact, in Minjay's case, he had an extremely difficult borderline paper, and he wrote, he wrote an extremely thorough, in my opinion, kind of level 5 review of the paper, which happened to be contradicted slightly some of the reviewers, but it was it was a really, really excellent review. Petter, of course, has been very involved in LOG since the start, and actually was one of the best reviewers, so best ACs last year. And Zhao Wen also really did some excellent work in as an AC. So thank you to the 3 of them for the incredible standard they set as ACs. Next, we have the reviewer awards. So the reviewer awards are, as many of you know, monetary awards at LOG. We pride ourselves on having the best reviews of any conference in the world. Well, perhaps. And the system at LOG, we ask authors and ACs to score all of the reviewers, and then we rank all of the reviewers based on these scores, and then we can manually, as PCs, go through the top sort of 10% and assess who is worthy of being the best reviewer at LOG, and then we award 10 prizes, and those 10 prizes are awarded to the people on the next slide. And I will read out their names: Francesco Di Giovanni, Alex Moorhead, Dobrik Georgiov, Yunan Liu, Rishi Sonthalia, James Nastos, Gesia Bravo Hermsdorf, Arjun Subramonian, Georgios Boristas, and Ralph Aboud. So congratulations to the 10 of you, really for going above and beyond what is normally expected of reviewers, and really putting in probably hours and hours of effort. What we looked for from a best reviewer was someone who actually improved the paper noticeably and also was extremely engaged throughout the rebuttal period, helping the authors, essentially helping the authors write better papers. And that's how this should work. And I'm very pleased with how it has worked this year. So thank you very much to those guys, and indeed to everyone who reviewed that log.
Thank you, Ben. And also, yeah, very exciting. I think especially my personal favorite part of the conference program is the ever-growing local meetups. I think that really demonstrate the need of local meetup and how people want the support from the local community and the engagement. So we have 13 local meetup, arise from last year 6 local meetups. Among 10 of them, they are happening around the same time as the conference, and 3 of them a little bit like early January, February next year. So there are one at Stanford, US, and there are one at Munich, Germany, Amsterdam, Netherlands, Shanghai, China, and Switzerland, Paris, France, Norway, Spain, and Beijing, China, Trento, Italy, and New York, US, and London, UK, and Montreal, Canada. Thank you so much for the effort of local organizers to make this happen and make us a strong conviction that people want local community. That's very proud. I'm very proud. We are very proud of this program. And without further ado, that's the end of the opening remark. Next, we are going to switch to our first keynote talk from Dr. Kristof Schütt. And I'm going to let Xinyu to introduce Dr. Kristof Schütt. Xinyu, take it away.
Yeah, I'm here. Yeah, thanks. Hi, everyone. I'm Xinyu from Milan. Actually, Yuan and that's the sponsor keynote session, which is coming next. Today, we have the privilege of welcoming our distinguished keynote speaker from Pfizer, Dr. Kristof Schütt. Dr. Schütt received his PhD in computer science on the topic of deep learning for quantum chemistry from the Technical University Berlin in 2018. After working on real-time speech enhancement for hearing aids at Audit, he became a group leader at Berlin Institute for the Foundation of Learning and Data until 2022. Currently, he is a research scientist at Pfizer, focusing on machine learning for drug discovery. His innovative work, including the popular SCHNet, has opened new research avenues for implementation learning. Today, Dr. Schütt will share his insights under the title Graph Learning for Chemical Discovery. Let's give a warm welcome for Dr. Schütt.
Hello, can you hear me?
Loud and clear.
Yeah.
Great. Yeah, thank you for having me. This is actually my first year at Pfizer, so I started 1st of January 2023. Before that, I was at TU. And today I want to talk to you a bit about graph learning for chemical discovery. And now I have to find out why the slide is not working. No, okay. Yes, so I will start a bit with some of my university work and then lead over to what we have been doing at Pfizer this year. So I'm part of the machine learning research group here in Berlin, and we are part of the larger group Machine Learning and Computational Science, which is based in Cambridge in Kendall Square. And so what you see here is part of a perspective in the Journal of Chemical Physics that we wrote at TU together with the Bauer group at University of Warwick. And the idea of this perspective was to basically give an overview over the workflow in computational chemistry, and then point out where we can apply machine learning. And we had this nice plot where we said, okay, first we need to model our system, so with quantum mechanics or some kind of force fields, and then we have the electronic structure calculations, and there again we can basically enhance those with machine learning. And then once you've done that, the next thing is you want to explore the chemical space, and that starts small with something like molecular dynamics here, where you basically just have the vibration of a molecule. You can go further to do some conformer sampling, so explore some structures, and then go even further to basically cover the whole chemical compound space. And in the end, you want to also do something applicable, so that you can connect what you predicted to the experiment. And two topics that relate to that I want to discuss today is one is high throughput screening, which we want to do at Pfizer for drug design. So that means we want to quickly scan to a lot of compounds and see which of those are possible drug candidates. And on the other side, I also want to talk a bit about inverse design and generative models. So that means instead of scanning through a lot of compounds, we want to directly generate compounds that are suitable candidates. And so the outline for today is, first I start talking a bit about representations for chemical systems. And we have a lot of traditional chemoinformatics techniques like fingerprints. And then, of course, we have these neural network solutions, so like Schütt, which I developed back in my PhD days, or PAIN, which is the equivariant extension of Schütt, and then EQGAT, which was introduced last year here at Learning on Graphs. And then I'm going to the generative models and virtual screening solutions. Yeah, okay. So since I was talking about chemical discovery, so here the idea is really to go across the whole chemical compound space. So if you on the right side have the local exploration, we have molecular dynamics where we have rotatable bonds and so on. Then on the opposite side is the whole chemical space where each of these small galaxies you see here in this illustration correspond to one compound in the space. And so how can we represent chemical compound? In about, I think in 2007, there was one of the first neural network potentials that was really scalable across multiples, across the number of atoms by Jörg Behler. And the idea there was to represent atom-centered environments by so-called atom-centered symmetry functions. And then you basically had a set of features for each atom. You put that through a fully connected neural network, and you would get an energy contribution for each of these atoms. And then to get the energy of the whole system, you would just sum up these energy contributions. And during my PhD, I basically said, okay, that was about 2017 or 16. Now we want to do something end-to-end, and there were already some graph neural networks around. They were not called message passing yet. That happened also in 2017, that the Kumo paper came out. And so the idea was then basically that we model the interactions between these atoms and then build up in this message passing fashion higher order of interactions to predict, to get a representation of an atom. So yeah, now this is called message passing. And in the Schütt, that was basically an alternative viewpoint to the same thing, because you see, once you have 3D coordinates of the molecular atoms, you don't have to see this. Don't have to see this just as a graph, but it's embedded in a Euclidean space. So you can also see this as a convolution in space, where instead of having a discrete filter in the in your convolution, you have now a continuous filter. And here in Schütt, it was basically restricted to these radial filters, so that you effectively only have a function over distances, which then allows you to get some smooth prediction of the energy. And what was also nice with this architecture back then was that we could learn embeddings of chemical elements. And if you then look at these embeddings, so here just the leading principal components, you see that actually the groups of the periodic tables cluster together, have some structure. So that means that just by starting with one hot encodings of chemical elements and the geometry and the prediction of the energy, we could basically learn some kind of structure of the periodic table, some part of the structure of the periodic table, to say. Okay, so we soon noticed that just having these radial functions was not enough. And there were various works that pointed that out. For example, there were the steerable CNN papers, and there were the tensor field neural networks. But for, I guess, technical reasons, these early works didn't quite perform as well as the invariant solution. So, and in 2021, we proposed the Payne equivariant message passing neural network. And the general idea is you can, with just invariant neural networks, you can reconstruct, you can represent the full geometry as long as you don't introduce a cutoff. If you introduce a cutoff, then you start, you miss some of the information. So here's an example. So you see these two structures here, where we have introduced a cutoff. And even with angles, so with angles and distances, if we have this kind of cutoff, we can't distinguish the structure on the left from the structure on the right. What you need here is some kind of directional information, or you would need to get basically to the next degree to the dihedral angles. But having these directions has some merit, because we can do that per atom and then propagate this kind of directional information across the molecule. So one example you see, one practical example you see on the right. So we have here a ferrocene system where you have two rings with the with an iron atom in the middle, and now you can start rotating these rings against each other, which leads to an energy profile you see here in gray. And if you only if you have a cutoff that's sufficiently small, then these two rings won't see each other because of the cutoff. But if we now include directional information as part of the network, then we can here in orange, that's the prediction by Payne, we can still capture this energy profile that you get from the rotations by just propagating the orientation of the rings over this iron atom in the middle. So the key how we do that is this vectorial convolution in Payne you see here, and that's basically a general formulation for that would be Clebsch-Gordon products. So actually this vectorial combination is a subset of the terms you would get in the Clebsch-Gordon products. And yeah, that means then, so we in Payne we treated this in a Cartesian way, but if you then go to Clebsch-Gordon products and strike harmonics, the nice thing is you can basically systematically go up to higher angular momenta and include more and more of this information. So some applications we use that for. So one of that was the computational spectroscopy. So running basically molecular dynamic simulations with the machine learning force fields we trained. Then we did that. We applied that to predicting molecule dynamics in solution, or also reactions, where we applied something that we called QMML. Sorry, MLMM. So there's a QMMM where you couple quantum mechanics with molecular mechanics, and we basically switched from the quantum mechanics method to a machine learning force field here, and still had the classical force field for the solution. And another application was this molecular manipulation, where we basically peeled molecules off a surface with a scanning tunneling microscope. Okay, but that was basically my old job, and now I want to slowly convert to the stuff we're doing at Pfizer now. And so building on Payne, last year Tuan Lee introduced the EQ-GATT equivariant graph attention here at Learning on Graphs. So Tuan is a PhD student currently working in the machine learning research group at Pfizer. And so the EQ-GATT basically builds very much on Payne, but now also includes attention mechanisms. So there are basically MLPs as part of this architecture that predicts attention weights. And so here you have the scalar channels S that operate on distances, and then you have the scaled relative atomic positions, PJI, and you have vectorial features, just like in Payne. But now you have this attention mechanism that acts both on the invariant features as well as the directional and vectorial features, and that allows you to better to turn down some of the aspects of the atomic environment. And also what EQ-GATT has, what Payne didn't have, is it's using cross products. So that means if you have two vectorial features that are oriented like that in a plane, you can basically move out of the plane, which would not be possible with the original Payne architecture. So this was applied to some atom 3D biomolecular benchmarks. So this benchmark has various, sorry, I'm a bit distracted by all these people plopping up that are entering the room. So that has several tasks on biomolecules, for example, protein structure ranking, RNA structure ranking, ligand binding affinity, residue identification or protein-protein interactions. And you see that here EQGAT outperforms PAIN and also the other architectures on most of these tasks. And the reason why I introduced EQGAT is actually because of some work we just finished, and this is primarily done by Tuan Le and Julian Kremer, who's also a PhD student in our group. And that's EQGAT diff. So now they applied this, this representation to diffusion models to do some 3D equivariant molecule diffusion. So here's, how can I click this again? Okay, I can't. Sorry. I think like this. Okay. So this is one trajectory, how a molecule in this framework was generated. So I guess most of us know diffusion models. So the idea here is that you have some complex distribution, and then you apply a diffusion process to get to a tractable prior distribution. And then the task for machine learning is to learn a backward model that takes you from a prior that you can sample from back to the complex distribution. And we are especially interested in de novo molecular design. So that means we want to jointly learn the molecular graph with the chemical elements and the bond topology, as well as the 3D coordinates. And the reason we also want the 3D coordinates is really that while we don't need, so first of all, we need to distinguish what conformer we get, but also these 3D coordinates give some additional information to the diffusion process. So instead of having just an abstract graph in some space, we have an embedded graph, which allows us to make some more, to apply some more constraints on the model. Now, the thing is to develop a diffusion model, there are some important design choices that one has to consider. And Tuan and Julian were basically trying to navigate the space of design choices to find out what's the optimal way to build a de novo diffusion model for molecules. And here is basically, these are the three main choices they explored. So one is continuous diffusion versus discrete diffusion. So for the atom position, it's clear it's a continuous variable to say, to have the position of the atom. But when it comes to the bonds between the atoms and the chemical elements, then these are discrete variables. So you could either treat them as well continuous, or you can use a discrete diffusion where you basically draw from a categorical distribution. So these are two ways to treat basically the bond graph. And then the other choice is how to parameterize the diffusion process, or the learning of the diffusion process. So you could either try to predict the noise that is added to the original data, or you could, so that would be here, this epsilon parametrization, or you can try to directly predict the original data x0. So X0 is the original data without noise, and XT would be then the diffused data. And as a third option, how do you weight the different time steps? And so that's basically the first parameter they try to determine. And so the standard baseline would be to say, okay, each step in this diffusion process, I give the same weight. But then there's also some time-dependent loss weighting based on the signal-to-noise ratio proposed by Salimans and Ho. And that would give you a weighting like this. So you have constant weighting for the first time steps, and then you have a decreasing weight for the higher time steps. And the intuition there would be, once you are in a domain where you have basically mostly noise in your data, it becomes very, very hard to directly predict X0. And it's also, since you denoise sample stepwise, it's also not as important to get the accurate, let's say, atom positions. But you have to basically just get somewhere in the ballpark, because in later steps in the sampling, you can still refine what you've got there. And so if we now compare the constant weighting and the time-dependent weighting, here we benchmark that on QM9 and Guillaume Druck's data set. And you see across multiple metrics, so we have here the molecular stability, the validity of the predicted generated molecules, and the connectivity. So we would like to have only one connected compound and not multiple small compounds. We see the time weighting really helps across all these metrics on both data sets. Okay, with that in mind, we can now look at the other design choices, so continuous diffusion versus discrete diffusion, and epsilon versus X0 parametrization. And what we found here is, if we apply the EQ-GATT diffusion model with X0 parameterization and discrete diffusion for the bonds and the atom types, we get here the best performance compared to X0 with continuous, or epsilon parameterization with continuous diffusion. Okay, so after that, we looked at additional improvements. So first of all, we're diffusing the atom positions and the bond graph simultaneously. So why not include further chemical features? And obvious candidates are the rings and the aromaticity, as well as the hybridization states of atoms. And if we do that, we see here in this table that we improve over multiple metrics on Guillaume Druck's. And also another idea would be that while for quantum chemical data, there's a rather comparatively small amount of 3D structures, there's something like PubChem 3D, which has a large amount of 3D structures that were relaxed with empirical methods. We said, okay, let's try to pre-train on this large data set and then transfer this to the more accurate 3D structures. And we noticed some curious thing, that if we train without explicit hydrogens on this PubChem 3D data set, and then transfer to Guillaume Druck's, which has explicit hydrogens, it works for some reason better than with training with explicit hydrogens on PubChem 3D first. So one hypothesis we have is that it's easier for the model to do to transfer from, so basically that the hydrogens have or the other way around, that the level of theory for the 3D position plays a significant role for the position of the hydrogens, and it's easier to add them in the fine-tuning than to adjust this position. But that's currently something still we're still looking into what's exactly the reason. But no matter what, it's really nice, because if you remove the hydrogens, the pre-training, since you have much less atoms, gets quite faster. Okay, here's an outlook on what's to come next. So of course, just generating molecules without any conditioning is a nice technical exercise, but not what we want to do in the end. So here on the left, you see conditioning on chemical properties. Here, just as a visual example, conditioning on the polarizability. That's always nice, because with you can see directly whether it worked, because if you have a high polarizability, you get these large, or these long structures, while with low polarizability, you get these more compact structures. And then, of course, what we want to do in the end is to directly do target-based drug design in a pocket. So here, this is repeat the video. This is a trajectory from EQGAT trained on the crosstalk data set, where we directly generate a molecule in the pocket. But yeah, this is still ongoing work. Okay, that was the first topic on generative AI in drug discovery, or well, not yet drug discovery, but hopefully soon. And now I want to talk a bit about virtual screening and a very exciting screening technology, which is DNA-encoded libraries. And this is work with Shane Grabowski, Hongyao Zhu, and Robert Stanton, all from our machine learning and computational science group. So what is a DNA-encoded library? We want to identify compounds that bind well to a certain target protein. And to do that, we need to conduct experiments. But if we want to measure a lot of molecules, yeah, it gets expensive and it takes time and it's costly. And DNA-encoded libraries are basically a high throughput screening method that allows us to test with billions of molecules at the same time. So in DNA-encoded library works like that. It has, so each compound has several building blocks that are synthesized one after the other. So you start off synthesizing the first building block. So let's say here we have almost 200 products that are possible for the first block. And then this is connected to a part of DNA. And this DNA serves basically as some kind of a barcode. So the idea is to test a lot of molecules at the same time, and later we can read out the barcode and identify which molecule has bound to the protein. So if we have these products, we basically put everything back together, mix everything, and then we have a second cycle where again a second building block is attached, and at the same time also a second part of DNA is attached here, building the barcode. And by that we have basically this combinatorial explosion possibilities how to build this kind of molecules. So in the end, here in this case, with 3 building blocks, we would have about 2 million pooled products, and attached DNA tag for that. So then this kind of library is applied for screening so that works like that. So we have, first of all, here in gray, you see what are called magnetic beads, and attached to these beads are the target proteins here, like that, with some pockets. And then the whole DNA encoded library is basically mixed with that, and the molecules that can bind to the target, attached to the pocket or somewhere else, and the rest is washed away. And now, in the end, we can basically detach the DNA tags from the compounds that have that stuck on the proteins, and then do some DNA sequencing, and then as data, what we get for our machine learning method later is read count. So for each molecule in our library, we get a count how many of those were measured by the sequencer. And one thing we have to be aware of is that the compounds can also stuck just to the beads and not to the proteins. And to eliminate those, we have several selection conditions, and one of them is the beads condition, in which we measure how many of each of these compounds stuck to the beads, so that when we measure the reads on the target, we can basically subtract the compound reads from the beads condition. And then we can also have several other selection conditions, for example, lower concentrated target, or we can have competing compounds to measure to find some allosteric pockets, or we can also have other targets, so off-target conditions, so that we can find out whether the compounds are specific to a certain protein. So at Pfizer, we have about 3.5 billion compounds in a total of 38 DNA encoded libraries. So that means we get a lot of compounds tested at the same time here. And the way this process works is first, the DAL libraries need to be designed and synthesized. And then after some pre-selection and validation, we go to this DAL selection process. After that, the DNA needs to be sequenced so that we know the reads for the compounds. And then there is data triage and analysis. So you get something like the 3D plot. So if you have 3 building blocks, you get basically, so this is basically the space of the whole DAL that you see here. And then if candidates have been identified, they need to be confirmed. So first, on DNA hit confirmation, that means with the compound still attached to a part of the DNA. After that has been done, it has to be confirmed that it also works without the DNA. And in the end, after this off DNA synthesis, there needs, of course, to be the test without the DNA. And you see that this process, after getting the data, also takes quite some time, and it requires additional synthesis. So there's an orthogonal idea to that. So that means when we get the data, instead we can use it to train a machine learning model and then predict on some in-house or commercial library of compounds that we can order and then test on these compounds. And here the advantage is we don't have to do the synthesis and the DNA hit confirmation. We can basically just train the model, prioritize the compounds in our library, and then purchase them, which is cheaper and faster, actually. And there has been some related work to that. So most notably, this paper, Machine Learning on DNA Encoded Libraries, a new paradigm for hit finding by McCloskey et al. So that was done by a collaboration of XChem and Google. And they showed that with a relatively simple approach with graph convolutional networks or random forest, they can identify quite some hits for 3 targets it shows here. So what's actually the difficult part here? And that's for one reason, it's the noise in the measurement here. So here you see a replicate of a L screen. So that means the experiment was repeated twice. And then you see here the log reads on the X and Y axis. So that means if it's on the diagonal, it would mean that both experiments would result in the same result. And this is generally the case if you go to higher read numbers. But in low read numbers, you see there's quite some noise. If the signal is weak, it's not clear that we can really trust the signal. And one other perspective of that is if we look at this kind of plot, which defines the space of the DEL library, each dot here would mean one compound in the library. So, for example, this one. But you see these lines, and this is typical that these lines form. And such a line feature is also called a disynthon. So that means if we have 3 building block libraries, 2 of them are fixed and 1 is kept variable, and then you have this line. And since we have the structure, it makes sense to look for these lines actually in the data, also to use that in the machine learning. Then, of course, you could also say, go one step further and even look at these planes where only one of the building blocks is fixed. So we looked at 3 kinds of representations. For one, the classic molecular fingerprints. So here we looked at the circular fingerprints, ECFP4. A nice thing is that they capture the local connectivity motifs using basically something like a fixed message passing and hashing scheme. And they are quite fast for training and inference since we can pre-compute them for our molecules. And then, of course, we looked at graph convolutional neural networks, assuming that they would be better at generalizing and adapting to the molecular graphs we have in our libraries. And as a third option, we also look at pre-trained embeddings using continuous data-driven descriptors. So these are basically taking one molecular representation and then through an encoder-decoder scheme predict another one, and by that learn very nice molecular descriptors in the latent space. After some initial experiments, we kind of disappointingly, we noticed that actually these molecular fingerprints work best, at least on our data. So that's so these experiments are what I'm now showing you. But of course, we're very much interested to going back to graph convolutions. Graph neural networks. Okay, so first our baseline was really similar to the Dyson approach in the McCloskey paper. So we start off by these Dysensons, then calculate our ECFB4 descriptors, and then just use a fully connected neural network to predict as a classifier to predict if we have a hit or if we don't have a hit. And the way we decided what's a hit is we have the normalized sum of the logarithmic reads, and there we take the ones from the target condition and then subtract them from the beats only condition, which is basically the compounds that stuck to the beats instead of the target. And then what's a bit problematic is we have to choose a cutoff, a threshold to say what we consider a hit. That was our baseline. It's nice that it's robust to label noise. Since we can define the threshold, we don't really have the problem with the low reads and the noise that they get. And the disadvantage is that we have to define this hit threshold and really look at the data and see what's a good threshold for a certain screen. And of course, we also ignore some of the information we have because with the classification and just having two classes, we ignore the recount differences within the classes. Moving on from that, so we looked at pairwise ranking, and also we looked at not applying this to Dysensons, but to the whole compounds. That means keeping all the information and not aggregating over one of the building blocks. And basically this part of the input, the descriptors in the neural network stay the same. Only loss changes. So now we're using a pairwise loss for pairwise ranking. So if we give a classifier a pair of molecules and give it the 0 class is if the first one has a larger number of reads, the 1 class if it's the other way around, and 0.5 when they're equal, which is mostly the case if both are 0, because the reads are pretty sparse, so most of them will be 0. And then it's just the standard classification loss. And now the advantage over the classification is that now we don't have to define this hit threshold, and we can also learn from all pairwise relations. So that means we also learn from differences within the classes. We don't have classes anymore, but basically consider all the reads. Okay, so now I'm showing you some results. So this is from some real project data from an internal project, and there was basically a data screen performed for this project and an experimental assay where the candidates from the data screen, but also from different methods were tested. And we basically do a retrospective on this, where we say we define the actives as the compounds with less than 1 micromolar concentration, and we evaluate our ML model by comparing these hits with 1 million about 1 million presumed inactive that we have in our internal Pfizer library, where we filtered the compounds that were structurally too close to the actives. And here is basically the comparison of the 3 methods I showed you. The baseline was a Dyson classifier, and you see, so here we have precision recall curves, and we get a nice precision with up to about 10% recall, but then it quickly drops to, so here in orange you see the prior of the positive class, and here in green you have the average precision. So it quickly drops for the classifier on the Dyson. Then in the middle you see now the ranking model, and that has a slightly lower average precision, but you see it quickly drops here, but then stays longer above the prior. And on the right side, you see the same method, but now trained directly on the compounds instead of the Dysensons. And we see now we get much higher precision at higher recalls. And also increase the average precision by 10% compared to the classifier and the Dyson ranking. So of course we are. This is a bit limited, this benchmark, because it's a retrospective, and some of the positives are, of course, influenced by the DEL. But we're currently doing some ongoing extensive validation on other projects, and see already some encouraging results that I unfortunately can't show you today. I get to my conclusions. So I showed you machine learning for DNA encoded libraries. So this is a very exciting screening technology for getting a lot of data for binding to protein targets. And I think there will be also public data, a lot of public data becoming available in the future. Currently, we're doing this on internal data. We found that ranking on compounds based on the fingerprints works best for us, but of course we're interested in, can GNNs do better? And can GNNs be fast in training and inference on billions of compounds? And the other topic I talked about was de novo 3D molecule generation, which is a very promising avenue to explore a larger chemical space where virtual screening is not feasible, because at some point when I have 10 to the power of 40 compounds that I want to screen, even the fastest machine learning method will take very, very long. I showed you unconditional generation and some outlook on conditional generation, but further research is needed, in particular when it comes to target-based drug design, and also what's not looked at a lot yet is synthesizability of the predicted compounds and how to constrain the space of generated molecular compounds. And with that, I thank you for attention, and I'm looking forward to your questions.
Hi, Kristof. I think we have one question in the Q&A session. Can you see that?
Okay, yeah. Okay, I can read the question. As some de novo design methods usually lead to some ridiculous molecules, like a lot of benzene ring, even the smiles in the graph is quite accurate. Even how can you mimic this? Okay. Well, I'm not quite sure what this could. So I think that relates to the synthesizability of the compounds. And yeah, it's true if you do de novo generation and you just train on some data set like even like the drugs, which is already quite constrained. The generation can lead to some very weird molecules. And I think that we need to find methods to really constrain the space of molecules we can generate, but that's, as far I know, still ongoing research, and I don't know whether there's already something yet published that really tackles this problem nicely.
Thanks for the answer. I think there is another question from YouTube channel where Brahom asked about I think the question should be like, because the first part of talk where you talk about the GNs and the Schütt and the have you ever tried to predict protein functions from structure with those GNs?
No, I did not. I don't know whether somebody in Pfizer did. I can say that, but personally, I did not. And but
I think maybe
I can imagine that it's doable in principle.
Sure, thanks. Yeah, I think maybe what he asked is about if it's doable. Yeah.
Okay.
I can ask a question. Like, I'm very curious about your perspective, because you have been developing this 3D GNs for molecular system since back then. You mentioned 2017. You were really a pioneer at that time. Like this field is really fast going for designing better GNs and covariant architectures these years. What do you think as the future and the unique challenges of this field, and as it continues to grow, what are the unique perspective you have in mind to make those problems, maybe some of the problems from unsolvable to solvable?
Yeah, I think scalability is still kind of a problem and not so much. I mean, there are two aspects when you design these equivariant neural networks. So one thing is everything that's within the cutoff, right? So having these short range interactions accurately modeled. And I think there we are pretty far. But when it comes to long range interactions or scaling to protein sized molecules, and then, I mean, simulation is one thing, but even if you do something like, want to predict something more coarse, like functions or something, some high level concepts, I think there's really still some innovation needed in basically going from atom-wise representations to more coarse representations in a very scalable fashion. I think that's where we still need to do some work.
Thank you.
I think we also have another question from the Slack channel. So I'll read it out. For diffusion-based generative models for small molecule generation, how well would you say that are the findings of your study transferable to other drug design settings? For example, protein pocket conditioned molecule generation.
So I think this transfer works pretty well of this architecture. We're having done some experiments on that, and I think on the open review version of the paper that I shouldn't point. So basically, there are some results that should also be soon on the archive. Yeah, and it seems to work well. That's what I can say. I mean, you've seen only this one example where I've seen only this. I showed only the one trajectory earlier here of the within the pocket on the crosstalk data set. But we have some results with docking information, and it seems to transfer well to that setting.
Yeah, thanks. Looking forward to the preprint soon. Yeah.
Yeah, I think Chaitanya has another question.
Yeah, I thanks for the awesome talk and for all the perspectives. So you presented these two approaches, right, of high throughput screening and then generative modeling. Just from your own, what are you more excited about for the future? Which ones do you think are more realistic, and what do you think is coming next?
I think virtual screening in the short term is the more realistic, and they are still, even when it comes to drug design, ligand binding, affinity prediction, and this kind of stuff, there are enough problems already there that we still need to solve. But of course, in the long term, if you want to really large chemical spaces, then we want to do de novo design, but there are then on top of the problems we first have to solve on the virtual screening end, these problems like synthesizability and weird molecules we're getting and so on. So basically, in the long term, I think de novo generative AI is the way to go. But there's still to get that practical, there are still some issues we need to solve even on the virtual screening end.
Yeah. Even for your work on virtual screening, right? Did you have any intuitions as to why these simple fingerprints were doing so well compared to, say, the graph neural networks?
So one thing is they are these. You basically have these one hot encoding hashing of these of subgroups. That means I think they're pretty robust to the size of the molecule, and especially with disynthrons, it's I think more robust to when, so you don't leave the training domain as fast as you would for GNNs. So it comes down a lot to robustness and the noise in the data, and also the sparsity of the reads. So because I mean, I think what was the prior, I think 0.35% were non-zero data points. I think that's an issue. So some kind of pre-training is probably required to solve this.
Yeah.
I think we have time for one last question from Alina. Are you able to? Would you like to text or you can just turn on your microphone? Alina? Seems she's not around. Okay, then I have a very quick last question. So talking about drug discovery, I think Pfizer has a lot of in-house data and the private data. I mean, at least from my perspective, I feel like Pfizer could. I mean, if we want to talk about virtual screening and training a super large foundation model for drug discovery, Pfizer is really in the good position to do that. How would you guys? Yeah, are you guys? I know you will keep it secret, but how do you guys think about this? As you have really a lot of good quality data and high throughput, wet lab to collect data for you guys. I just want to know your comments on this kind of thing.
Well, I mean, I'm not responsible for the data. I'm just when applying the methods. So I think there's quite some good public data, and I think there will be soon more public data available, not from Pfizer side, but from different sides. Yeah, I think for pre-training large models, I wouldn't really worry too much about the the measurements, I would rather go for actually learning, yeah, some like I said with the proteins, to learn some higher level constraint like protein functions, this kind of stuff, or even something, yeah, the typical self-supervised pre-training task and building models from that, and then fine-tuning on a certain screen.
Thank you.
And
yes,
with
thank you
that, we
for
can thank our
question.
speaker, right? Thanks, Kristof, for an awesome presentation. And now I think we'll have the next keynote as well. So if you could stop sharing your screen, then Professor Jure Leskovec can start sharing his screen as well now.
Hi, everyone. Can you see my screen?
Yes, and we can hear you loud and clear as well. All right, so let's begin then. It's my pleasure to introduce Professor Jure Leskovec. Jure is Professor of Computer Science at Stanford University, as well as co-founder and chief scientist at Kumo AI. Jure's research is about applied machine learning for large interconnected systems, such as graphs and networks at all scales, from interactions of proteins in a cell to interactions of between humans in a society. I think it's safe to say that Jure is a pioneer of graph machine learning. So it's our honor to welcome him as keynote speaker for the second edition of LOG. And with that, Jure, please take it away.
Yeah, hi, everyone. Thank you for having me, and really excited to talk to you today. And what you are going to see is, I hope, something very interesting, something very transformative for the field of graph machine learning. And it's also something I've been, working on for the last 2 years, very quietly. But I think now it's kind of time to open it up and reveal it to the rest of the world. So this is kind of important for today. And what I'll be talking about is I titled Relational Deep Learning. And you'll see as I'll start very general, but the graphs are going to come in very, very quickly. And then maybe the last thing to say is this has really been a joint work with a number of people, Matthias, Weihua, Keshin, Jan, Rishab, Josh, Rex, and Joshwan. And I had the privilege to work with them over a number of years now. Okay, so here's now the talk, and here is kind of how we will start. Right, so we are kind of in the middle of the deep learning AI revolution. Right, it kind of started with convolutional neural networks and breakthroughs and superhuman performance in computer vision, and then it continued through kind of similar success in natural language understanding, large language models, foundations, the foundation models, and all fueled by the transformer architecture trained on a lot of data. So, what would you say is the most valuable resource today? It's actually the data, right? The data is the most valuable resource. And we train a lot of these large-scale language models and so on, and vision models on open source data, on data that is on the internet and so on. But what I would like to say is that actually there is one even more common and more important and more impactful data type out there, which is basically private data that is stored in a form of relational tables, that is stored in modern databases, data warehouses, where basically data is laid out in a form of tables, and these tables are interlinked with primary foreign key relationships. So really what I'm interested in is, how do we open, in some sense, the power of deep learning to this most common data type in the world, which is a set of relational tables interlinked with primary foreign key relations. And there's a lot of kind of, once you have this data in this type of form, there's a lot of very interesting and impactful questions you can ask over this data, especially in terms of building predictive, let's say, task-specific AI models. So, for example, even this simple schema that I'll be using throughout my talk of just 3 tables: users, transactions or sales, and products. So basically just recording which person buys which product. You could ask a number of different impactful business problems here. You could say, which products will a user purchase in the next 7 days? So basically that's almost like a recommender system. You could say, is a given customer going to churn in the next 90 days? So basically saying, will the customer not buy anything in the next 3 months? Or, for example, if you want to optimize your inventory, you would say, what will be the total sales of each of my products in the next 30 days? So you can kind of optimize the inventory and so on. So these are some examples on this type of schema. For example, a different schema maybe in a hospital where you have patients, admissions, notes, procedures, diagnosis. You could also ask a lot of very impactful predictive questions. You could say, if I discharge a patient, will a patient return back to the hospital? So am I safe to discharge a patient? Or, which hospital admissions have the greatest risk to life in the next 24 hours, right? So could I kind of predict that some people I admitted into the hospital need special care because there is this elevated risk, right? All these type of questions that I ask here are inherently predictive, and they are asked over this data coming in this relational tabular form where it's spread across multiple tables, and we have this notion of a primary foreign key relation that makes all these tables connected. And if you want to do AI or machine learning over this type of data today, kind of the state of the art is not kind of too encouraging. Basically, it takes team between 6 months to 12 months to go from deciding on the data to use, to build all the features, to train the models and be able to put them in production. So it's extremely slow and brittle process. So why is it that way? What is missing? The reason why it is this way is because there is this kind of impedance mismatch between how the data is naturally laid out and stored, and how machine learning models or AI methods can ingest this data to learn over it, right? So imagine I want to learn a model of churn behavior based on the person's sales, purchased products, web browsing behavior, sessions, views, and so on. And I have a schema here. And the problem is that today there is no machine learning method or no AI method that you could just apply to the set of these tables that could learn from it. What you have to do is you have to take these tables and massage them, join them into a single table. Basically, what you have to do is you have to do manual feature engineering. And you could say that, what predicts users' churn is maybe the number of sales, number of products they buy in the last month. Maybe it is the sum of weekly item prices they have purchased. Maybe it is, the number of orders they order on a Saturday versus the number of orders they order in a Monday. I'll take this ratio and this will be the feature. So you can see how I can basically compute a gazillion of statistics over these tables, put them into a single table and then apply my favorite machine learning method over this. And the problem in this is that it's super slow. These features are generated arbitrarily. Basically, there are some arbitrary statistics of the data. We are essentially throwing data and signal away because we have this rich data here on the left, and now we are summarizing it to this kind of single table arbitrary set of statistics. And this process is also kind of complicated and leads to a lot of problems with point-in-time correctness and things like that, because these tasks are naturally temporal, as I'm going to discuss later. So what does this mean? What's the key question? The key question is, how do we leverage data without going through these long duration tasks of extraction, transformation, and loading, basically feature engineering? And we wanna have machine learning algorithms that can process its data in the natural form, like the way the data is represented, the way the data is stored. if you see kind of what's happening in the broader field of AI, exactly this trend has been happening, right? In the classical computer vision, you would do your handcrafted features, you would compute your Gabor filters, whatever, and then you would train a classifier, an SVM, on XGBoost, whatever, to predict what is in the image. This is how old school computer vision used to be. Today, nobody in the right mind would try to do that. Today, you would take a deep neural network, point it directly to the pixels of the image, and train that neural network in an end-to-end data-driven way to give you the predictions you want. So the question is, can we do this, or how could we do this over the tabular data? So really what I'm interested to talk to you today about is, how would you take this most common data format out there in the world that stores the most valuable data, the most important data, but we have no good way to do deep learning over. And we still have to do manual feature engineering, and kind of this area is still in this pre-deep learning, pre-representation learning era. So the question is, how would you do this? So this is the area that I want to call relational deep learning. It's really the field of how do I do end-to-end deep learning? How do I do representation learning over a relational database? Or how do I do deep learning over a set of interconnected tables, relational tables? We want to work directly on the relational tables. We don't want to do any transformations. We don't want to do any feature engineering. And we want to, basically the way the solution will be is that we are going to cast these predictive tasks as graph representation learning problems. And what I want to achieve in this talk today is first show you the exciting problems in this area and very rich, interesting research questions that are still open and that community can solve. So basically, I see it as a way to generalize, in some sense, the applicability of graph machine learning beyond social networks, and really say, as soon as you have data stored in more than 2 tables, graph machine learning is your friend, right? So anyone who's running a data warehouse, anyone who's running a database should be using graph machine learning to build predictive models over their database. That's the kind of the exciting part here. It's the amount of applications, impactful problems we can solve with graph machine learning, okay? And that's what I'm trying to say for today. So, if you were able to apply, let's say, deep learning over this type of tabular data, why would it matter? And here are a few reasons why it would really matter. First, your models would be much, much more accurate, right? You wouldn't only learn over these arbitrary summaries of the data, these features, but you actually learn over the entire data that contains all the signals. So kind of the same boost that computer vision went from, subhuman performance to superhuman performance. Now that's ready for you to do on your relational data, on your business data. Your models actually become more robust because, especially when the data is changing over time, when new events, transactions are arriving into databases, traditional machine learning models will get obsolete because features get obsolete, and you have to constantly engineering new features. Here in this world where representation is automatically learned by the neural network, you can just retrain the model. So the model kind of naturally updates over time. Because these long mundane duration tasks are now gone, it is much shorter time to get to the models. And it also kind of on the broader scale simplifies the entire infrastructure. You don't need ETL pipelines, you don't need feature stores or anything like that anymore. So it's much easier to put models in production. So what are some examples of related work about what I'm going to talk about today? So the first piece of related work is the area of tabular machine learning, right? And you would say, hey, Jure, you are just talking about tables, so doesn't tabular machine learning solve this? I would think it does, but actually it doesn't. The reason is that tabular machine learning focuses on learning from a single table, right? But most of the data out there doesn't come in a single table. It comes in multiple tables. So for this reason, you have to manually convert the data across multiple tables into a single table data. So you have to do feature engineering, which is actually the bottleneck. Our hypothesis is also actually here is that people have observed that deep learning does not perform well when trained over a single table. So basically, deep learning methods are not performing well in tabular machine learning. And our hypothesis for that is that because, you know, a single table already contains feature engineered from other tables, you have lost so much information that there is not too much opportunity to do representation learning anyway. So the relational deep learning that I'm going to talk about today basically generalizes tabular machine learning because it accounts for relations between multiple tables. And it really allows you now to apply representation learning to data that is spread across multiple tables. Actually, probably the most related work to what I'm going to discuss today is the field of statistical relational learning. So this was pioneered by Daphne Kohler and colleagues here at Stanford. You know, back in the day, about 20 years ago, 25 years ago, when they were trying to learn distributions, basically graphical models over the relational structure. And the way, right, back then in the day of the Bayesian neural networks and so on, you know, they were modeling these, basically said, we want to define a distribution over all the values in a relational database. And then we are able to make predictions via this kind of world model over the database plus inductive logic programming. The issue was that this only worked for categorical variables, and because every entry was modeled as a probability distribution, and then there was an entire Bayesian network over that, this didn't really scale to large data sets. So in this respect, the relational deep learning is a scalable, expressive inheritor of statistical relational learning. So now let me tell you, how do you do this, and kind of what's the idea? Okay. So the insight, as I kind of indicated earlier, is that your data is a graph, and you can look at the schema and say, this schema has, you know, three tables, so probably these are three nodes, and there is, you know, connections between these nodes. But really, I think the key insight is that it's not that the schema looks as a graph, but actually that your data spread across tables is a graph. So I'll be more formal later, but what you can do is you can take your tables, primary foreign key relations between them, and at the most kind of simple level, you can take every line, every row from every table and write it out as a node. And then primary foreign key relations act as edges between these different node types, right? So for every user in my database, I'm going to create a user node. For every product in my database, I'm going to create a product node. And now for every transaction has a product ID and it has a user ID. So user ID points to the user and product ID points to the product that was purchased as part of this transaction. So I can now create a transaction node that points to the user and points to the product. So now I have this kind of tripartite structure here of users, sales, and product. So now this is beautiful, right? Because now I know how to do deep learning over this relational database. I can take the relational database, represent it as a graph, and I can now directly apply deep, let's say, graph neural networks to essentially do representation learning for me without needing to do any feature engineering. What is also super cool is that the language of graph machine learning problems is quite rich. I can define predictions at the level of a single node. So this, for example, would be, I want to maybe predict the churn of a user, probability this person is going to churn, is not going to buy anything anymore. Maybe I can predict what is called the lifetime value of a user, which is how much are they predicted or forecasted to buy in the next few months. Or I could say, build a predictor about what is the next best action to take on a given user. Even product sales forecasting is still just simply a node level prediction task, in this case, a regression task. Interestingly, also, link level tasks are very important when working with tabular data. So if you think about recommendations, recommender systems, product affinity prediction, and things like that, those are just pairwise predictions between two pairs of entities, between let's say, the user entity and the product entity. And you can even take this further and define graph level tasks around, identifying fraud, anti-money laundering, and things like that, right? So kind of my point is that the space of graph machine learning tasks is more than rich enough to be able to cover the tasks that are interesting to solve when you think about relational databases and predictions over them. Okay. So now let me I want to go a bit deeper into the approach and show you how we can do this. So the first thing is that we need to decide what's the predictive problem we would like to solve. So the first step will be, let's define a task. And let's maybe say that the task we want to define is how much will each customer buy in the next 90 days? Maybe like we could say, how many products are they going to buy? The way I could do this is that I would basically use historical data to create what I'll call a training table, which would define let's say for every user, how many products are they going to buy in the next 90 days. Now that I have created this training table, I can connect it back to my schema, to my 3 customers, products, and sales table. And now I actually now have the labels, and I can train, let's say, a graph neural network to predict the labels as defined by the training table. Okay, so that's kind of the steps. So first, we need to define a task. So let's say we want to predict whether a user is going to churn in the next 30 days. The important thing here is that most tasks are actually temporal. Temporal in a sense that prediction whether a user is going to churn is different for different days or for different months of the year, if I think of it historically, right? A user's label is going to churn depending on the time. And also, the database changes over time. So if I think about traditional feature engineering, it's not only enough to compute the feature once, but essentially for every day of the year, I need to compute recompute the feature for that same user, because the behavior of the users is kind of changing over time. So in order for us to be able to do this, we need to define a task. And to define a task, we will need to be able to create what we will call a training table. And a training table will essentially contain 3 columns. We need to define what is the entity, what's the entity type for which we are making the prediction. We need a label for that entity. This is the value that we will be predicting. And we need the time of that label, right? In a sense that, user might churn, but then they might come back, and then they may churn again. So the user is going to have multiple labels depending on different times. Now that a task has been defined, we need to create what is called a training table, which is a special table containing training labels. As I said, it contains an entity ID, time, and then the label. And then the label could be, let's say, a binary label, and we are talking about binary classification. It could be a real valued number, and now we have regression. It could be some kind of multi-class, multi-label type thing, as you like. And as I said, this notion of time column is essential for this temporal prediction task, because an entity might have different labels at different times. And we can only, when training the model, we can only use the information up to the time of that entity, of that label. We don't want to be kind of learning from the future and having information leakage. So going back for us, right, we have our schema. Our prediction task is to predict whether the user is going to churn, which would be, for example, to say we want to predict whether a user is going to have 0 sales in the next 30 days. And we can kind of use historical data that for, let's say, every day of the year, we can say, is a user buying something in the next 30 days? Yes, no. And then we move the window forward for a day, and we ask the same question. And that kind of generates almost like a sequence of labels for that user. Now that we have basically defined this notion of a training table, what are we going to do is the following, is we are going to take our data, our sales, customers, products, and the training table, and we are going to represent this in a graph that we are going to call a relational entity graph. And after the data is represented in a graph and the training table basically defines the labels, then the graph neural network can be applied to actually automatically learn how to predict those labels. Those are kind of the 4 steps of this approach. So how are we creating the graph? The entity relational entity graph is that for a given database of tables, we have a collection of tables and a set of primary foreign key relations L between them. Basically, each table has a set of entities. These are basically the primary keys in that table, and each table basically defines a different node type. And the graph is such basically that the set of nodes is defined by all the rows, by the union of all the rows in all tables. So every row in every table defines a node. Every table defines a different node type. And then edges are defined by connecting to entities whose primary and foreign keys match, right? So if a user has a primary key user ID that matches as a foreign key into the transactions table, then there is an edge between the node representing that user and a node representing that specific transaction. So as I showed earlier, in our case, every user becomes a node, every transaction becomes a node, and every product becomes a node. And then edges simply link users to transactions, and transactions link to products, right? This is the case here, where we have this kind of one-to-many or many-to-one relations, and we have this kind of tripartite graph structure. But of course, you could also do many-to-many and so on. So this is kind of fully general. Now that we have created the relational entity graph, the next step is to connect the training table. So the way the training table will connect is that basically for different times, a node gets different labels. So maybe this person was churned in May because they haven't bought anything, but they actually came back in June and bought something. So for the month of June, they are actually an active user. They have not churned, and so on and so forth. What is kind of beautiful here, as I'm reading some questions people are asking, is that here no joins are required, right? Like, for example, the problem is if you'd say, okay, let me take the users table, join it with a sales table, and then let me join that with a products table. What I get is the row in that table will be basically users cross transactions cross products, right? And that's not what I'm predicting over. In this case, I want to be predicting over users. So what you'd have to do first is join these 3 tables together, and then you'd have to aggregate the values. And then when you aggregate the values, you don't know how to aggregate them, right? If I say I want to predict at the user level, I need to aggregate transactions. Transaction column has maybe 15 different transactions table has 15 different columns. I have the price, I have the time, I have the currency, I have the method of payment, and things like that, right? So how do I aggregate all that? Do I take the average? Do I take the minimum? Do I take the maximum? Do I take the standard deviation? Very much unclear, right? So joining these things just blows up the data, and it's kind of useless, right? So that's why you cannot do an outer join and do the MLP, because if you do the outer join, that's not the table will basically be, every row there will be user cross transaction cross product, and we are not predicting at that triplet level. We are predicting at the level of a single user. So that needs to be collapsed. You need to figure out how to aggregate this. There's 7 ways to aggregate that. Your data has exploded, and you are kind of for all practical purposes, that's not possible. Okay, so this is what I wanted to say. So now, how do GNNs fit into this? Is that basically what you can do is you now take the columns of your tables, and the columns basically define the attributes, right? All the properties of the user, everything I know about the user, that are basically the properties, the attributes of the user node. Everything I know about the transaction, those are properties of the transaction node. And everything I know about the product, description, categorization, and so on, those are properties of the product node. And now how will a GNN operate? A GNN will say, I'm trying to predict the churn label in May of 2023, let's say. then it is going to go through the graph, but it's only going to learn from the nodes that happen before this timestamp of May 2023. So it's going to learn how to aggregate this particular transaction and this particular product. Now, as we run the time forward, go to the second label of this person from June 2023. Now we can learn from the transaction that happened in May, and I can also learn from the transaction that happened in June. So basically, what I get here is I get this temporal machine learning for free without any issue, right? So now, if you say, how does the GNN operate compared to feature engineering, right? Basically, feature engineering is a join plus an aggregation, and it's a join over two tables over let's say, and then the aggregation happens over some fixed time window, and you can pick any aggregation you like, and you can pick any kind of time window you like, and that's why you get the explosion in terms of our number of features you can create. But here, basically, the GNN aggregation, in a GNN, we have the message arrives and then it gets aggregated. So the GNN aggregation is basically a learnable version of handcrafted features. So it's given better performance because these features are now learned through back propagation, right? And what I try to show here is an example how basically GNN is a neural version of a join plus an aggregation. Because in a GNN, we take the children row, we encode it, learn how to transform that into the message, and then the aggregation function aggregates these different messages, right? So, for example, this means that a GNN can easily learn, what is the sum of the product values in the last month that the person has bought, or whatever else the GNN, or whatever else is predictive of the task you are doing. The GNN is able to learn that. Right? So that's the beautiful thing. Essentially, now you have a neural version of a join plus aggregation where you never need to use the slow database to actually perform the join in the first place. But all this is learned through the neurons. Okay, so what are some benefits? The benefits are that the GNNs learn how to aggregate information. They can discard neighboring node information that is irrelevant for a given downstream task. So you don't have to kind of worry about that. And they can detect fine-grained patterns within local neighborhoods that manually you'd never be able to discover, right? It can kind of find a signal 3 tables or 4 tables away and bring it to the entity of interest to make an accurate prediction. Another interesting thing is that GNNs exchange information across training examples. What does this mean is that now training examples are not isolated because there exists an interdependency between entities. So, for example, a GNN will naturally have this kind of collaborative filtering capability where it can learn that users with similar features show similar types of behaviors. And the GNN can use these features to enrich the representation of a given entity for which we are making a prediction. Another important benefit of GNNs is this notion of multi-hop reasoning across table boundaries that can catch information which is hard to pre-compute beforehand, or which we as humans we would never come up with, with a feature that is a combination of 3 joins. So training tables in our case are tightly coupled with the entity we are making predictions for, and then the rest is for the neural network to kind of bring the information across these tables to the target table to make an accurate prediction. And then the last thing I want to mention in terms of benefits is that now basically temporal learning comes for free, right? So basically you are able to capture fine-grained relative and seasonal features via temporal embeddings, and you avoid data and information leakage because you are learning directly over the data, and you are just accounting for different timestamps. And the way you account for different timestamps is to say, if I'm right now at a given node and I know the label of that node at time t, then I cannot look at the transaction of this, let's say, user at that happened at time t+1. I can only look at transactions that have happened before time capital T. And this way, you basically never learn from the future, you only learn from the past, and you never create a bug, you never have this time travel or information leakage problem, because the GNN sampling can be such that you can only sample from the nodes that happen from the past relative to the current time of that label. That's kind of very important in practice, because most of the problems in the real world kind of are temporal, happen over time. So we have actually just finished describing all this exciting research vision, and we have published it at this URL at Stanford, and we are also going to post it on archive in the next day or two. But if what I showed is interesting to you and you want to kind of read about it, here's the paper. We just finished editing it, and it's available at this website, relbench.stanford.edu. Okay, so that's the first thing I wanted to say. The second thing I wanted to say is that it's not enough to kind of give you an exciting direction for research, but we also need to have data sets and benchmarks so we can track progress. So we, together with the team, have been working really hard to build a relational deep learning benchmark, basically a collection of data sets and prediction problems over relational databases, so basically over multiple tables. And today I'm really excited because we are announcing and launching this as part of this talk. So we are introducing this benchmark that comes with a set of relational databases, so basically data sets that span multiple tables, comes with data, tasks, and graph loaders, so basically we give all the code and things like that, and also comes with some relational deep learning models, in particular PyG and PyTorch Frame, as well as with evaluators to track progress and scores. So we basically give you the code to automatically download data sets, load databases and tasks, so training tables. We have a standardized evaluation protocol that prevents temporal leakage from the test set. And we provide you a framework agnostic data structures that you can use in your favorite ML stack. So that's the exciting part. Another part is that we provide integration both with PyTorch Frame as well as the PyTorch Geometric or PyG. PyTorch Frame is actually our new open source package that allows you basically to encode rows in a table. So basically you use PyTorch Frame to encode a row in a given table, so basically to encode all the attributes of a node, and then you use PyG, so graph neural network, to learn the message passing across these different nodes in the heterogeneous relational entity graph. And this way allow you to train the GNN end-to-end. We also allow for temporal neighbor sampling. That's also a feature we implemented in PyG. And as I said, you can use PyTorch Frame to encode the tables, which is also very useful and very exciting. Now, what data sets do we support? So RelBench is kind of, I would say, work in progress. And right now we have 2 data sets that we are very happy to include into the benchmark. And we hope that with the help with the community, we can add additional data sets to the benchmark. So if you have interesting relational data sets you'd like to contribute to the benchmark, please come talk to us. But the 2 we are able to release today is, one is the Amazon reviews, where we basically have a users table, we have the reviews table, and we have the products table, right? And for example, each review has a timestamp, time of the review, which customer contributed it, what product they reviewed, and then what was the rating, whether the review was verified, what's the text of the review, and what's the summary. And then, for example, for every product, we know the ID, category, brand, title, description, and price, right? And this is now a nice three-table schema. And the size is about 24 million entities, so about 24 million rows across these 3 tables. So not too large so that it's easy to work with. And then another one that's very interesting is the Stack Exchange. So basically Stack Overflow and Friends, where basically we have users and votes and badges and posts and comments and post history and post links. So now this creates a very interesting schema of 7 different tables over 5 million different entities with many different prediction tasks that you can define over these tables. So these are the first 2 data sets, part of the benchmark. But as I said, we are planning to release more. And if you'd like to contribute, please reach out to us. Now, what are the prediction tasks over these 2 data sets? We defined 2 prediction tasks for each of the 2 data sets. For the Amazon one, we do a churn, which would be predict whether a user is not going to review any products in the next X days. And then the other one is we call LTV, lifetime value, which is the regression, which means predict how many products a user is going to review in the next half a year or in the next 1 year. And then for the Stack Exchange, we are having 2 prediction tasks. One is a classification task: will a user make a post, comment, or a vote in the near future? And the second one is will a user upvote a post or not? So right now our tasks are mostly classification and regression. But in the future, we are also going to add link prediction tasks, so kind of recommendation tasks, which would be, will a user post in a given community, would be one example, or will a user review a given product, or will a user review a given product category, and so on. So this is also something that we are going to add over time. Just saying, using this rel bench is very easy. Just pip install it. You can load the data sets and start playing with it. What we also see, just as an example, is that the GNNs heavily outperform, let's say, these traditional tabular machine learning methods because they can learn from multiple tables, right? So, for example, the Stack Exchange engagement problem, where we want to predict if a user will engage with the website let's say here in the next 2 years. The GNN achieves the AUC of 0.84, while the XGBoost over a single entity table would only give you 0.6. So basically, the power of this is that you can efficiently learn over multiple tables without any manual feature engineering to accurately predict the label of your choice. So see the website to get started. Very excited about this. The second thing I want to mention is that actually, even before we wrote a paper about this, we founded a company. So Kumo is a startup I'm working on that implements this relational deep learning paradigm that I was talking to you about. So we've been working on Kumo for 2 years to build a large-scale graph machine learning platform that basically allows you to just point to your data warehouse, be it Snowflake, Databricks, Google Cloud, Redshift, whatever, register a set of relational tables, and now be able to build any kind of predictive model on top of that relational schema in a super easy, fast, and scalable way. One more super cool thing we have at Kumo is that we have developed a predictive declarative language called predictive query, which basically looks like SQL, but allows you to very efficiently define machine learning problems. So you don't even have to manually create a training table, but the training table gets automatically created for you through this language. So for example, if you'd like to build a churn model to predict whether a user will have 0 transactions in the next 30 days, in the predictive query language, you would just say predict count sales.star 30 days in the future, so 0 to 30 days equals to 0 for each users.user ID, right? So I'm saying for every user entity, predict whether the count of sales 30 days in the future is going to be 0. You could, for example, build more complex models super easily. You could say predict whether the last time I've seen a user and their tier status is going to be set to paid in the next 30 days for each user's .user ID, where the current tier status in the last 30 days was free, right? So I'm saying for all the users who currently are in the free tier, will they convert to the paid tier in the next 30 days? And from this specification, automatically a training table gets generated, gets attached to the tables, and a GNN gives you predictions. And similarly, you can build recommender systems by saying predict, least distinct. In this case, could be sales.product ID, 30 days in the future for each user's .user ID. And again, out of this, I basically say this is a link prediction task where I'm predicting an affinity between a user ID and a product ID. And we have this platform up and running and providing a lot of different use cases. What is happening here under the hood is very similar to what I've been saying. Basically, Kumo will ingest your tabular schema, represent it as a graph. It's going to take the predictive query, interpret it, and automatically generate a training table. And now a graph neural network is going to be applied to predict the labels in the training table from all the tables in your schema that you have generated, as well as their columns. What we see is that people are really able to achieve great results with this platform. So for example, a large financial institution in US was able to build a next best action type model for their customers in 4 days. In a single day, they were able to use Kumo to match their to basically match the performance of their internal model. And 3 days later, with more data, a bit more of AutoML search, they were able to improve the accuracy by 73% or 76%, sorry, right? So you see that very quickly, they were able to iterate and build a much more accurate model than what, their previous approach was. Here's another example of a large food delivery business who wanted to build a try something new type recommendation engine. They used Kumo to do this, and they benchmarked against their internal solution. They found out that the graph neural network across their set of tables was much more accurate than their internal model, led to more than 100 million of additional revenue for them in a year. And interestingly, graph neural network was actually 5 times cheaper to serve than their internal model. And the last one, the last success I want to show is similar. It was a large e-commerce platform where they were doing user to merchant affinity prediction. So what merchant a user is going to buy from. Here, in 3 days, they were able to increase the performance of the model by 22% given where they were. So basically, the point that I'm trying to make is that with graph neural networks, you can really learn over a set of relational tables very, very efficiently. And the same benefits or the same transformation that computer vision and natural language understanding went through when it went from manual feature engineering to end-to-end deep learned systems, now with essentially this very simple idea of saying, take the tables, represent them as a graph. Now you can apply this to any data warehouse in the world. So you can basically apply now representation learning to the most common and the most valuable data, most important business problems out there in the world. Okay, so this is what I wanted to tell you. And maybe before I conclude, just we have summer internship positions available at Kumo. We have apprenticeship positions available at Kumo, and we are also hiring full-time people. We have offices both in Europe as well as in California, in Silicon Valley. So to conclude, so today I wanted to get you excited about this notion of relational deep learning, where we want to do representation learning on relational data using graph neural networks. And I think this is extremely exciting because relational schema is kind of the most common data type in the world. And representation learning is on the relational schema is basically doing deep learning on the natural representation of the data with great benefits and improvements over state-of-the-art in machine learning over these types of data. So what are some key takeaways? First important takeaway is that basically now we have the ability to learn over all the data, in a sense that GNNs can learn over the entire data schema and, in some sense, learn to discard unneeded tables. So you don't need to do any feature engineering or some kind of manual statistics over the data. GNNs allow you to reason across multiple hops and capture patterns that are hard to pre-compute as input features or kind of impossible to come up with and hand engineer as humans, similar to what happened in computer vision. Because there's no manual feature engineering needed, now you are able to do machine learning over tables without joins, and basically it's the neurons of the neural network that learn how to combine the data. What does this mean? It means that your models all of a sudden become much, much more accurate, much faster to build, much easier to operate. So, but this is just the beginning. I think the key point of my talk today is that there is a huge number of interesting, exciting questions that remain unsolved, right? And I think, the first one is, what's the best way to represent database as a graph, right? I gave you kind of a rough idea how the representation looks like, but graph is constructed from a set of tables via foreign primary key relationships. But graphs constructed from database schema might not be the optimal for machine learning, right? Like you may want to collapse many-to-many tables. You may want to add additional connections between tables that are far away from each other via meta paths to enable kind of more optimal message passing. You could add additional intra-table connections to capture behavior of related entities, right? So there is a lot of interesting open questions here to say, what's the best way to represent database as a graph to enable graph neural networks over these relational databases? So kind of first broad, big open question. Second interesting open question is then, what GNN architectures are best suited for such database graphs? For example, what we find out is that these simple architectures that use a single aggregation function are not powerful enough. And we find that, for example, using multiple types of aggregations and fusing them together, as well as having rich heterogeneous encoders of columns, really leads to much better performance. So really, I think another kind of hugely open question is, what are good architectures? Be it a GNN or not, doesn't matter, that you could apply to this to really allow you to learn across the tables. I think what is beautiful in this case is also an opportunity to really rethink AutoML and to rethink, let's say, foundation models and so on. Because the interesting thing here is that once you have a schema, you can now define multiple prediction tasks on the same database. You can make predictions about users, you can make predictions about transactions, you can make predictions about products, all on the same schema. So it becomes very interesting. How do we transfer architectural knowledge? How would we, for example, pre-train, or how could we jointly train these models across multiple tasks, hopefully give even better and more accurate models? Right, so this kind of leads me to this question is, what is the role of pre-training? What is the role of transfer learning? Should each training table be a separate model? Should we train a single neural network that can make predictions across multiple training tables? And should we now start thinking about what's the foundation model for the graph data? Because now we could take any database, represent it as a graph, any set of training tables, and see if you can build a large pre-trained models that is able to answer these types of questions. And then I think another kind of the last thing I want to mention as an open question is, how do we harness the special structure of the relational entity graph, right? Because it is not like natural graphs. It has this kind of interesting M-partite-like structure. And so it's kind of more structured than natural graphs, but not super structured in some sense, right? So how could this structure be harnessed? For example, for large-scale graph machine learning, where you can distribute and partition the graph and be able to learn over it. How could this be harnessed for GNN architecture design, search, pre-training, and so on, right? So what I want to say is these graphs are a bit special. This special structure for sure can be harnessed to build better models, better solutions, more scalable models, different GNN architectures, and so on. So to conclude, today I introduced this, I would say, new field of machine learning called relational deep learning, where we want to basically build and allow for representation learning over a database, basically, which means over a collection of tables linked with primary foreign key relations. And I gave you one possible solution to this problem by basically taking the database, representing it as a graph, and then applying graph neural network to them. And by doing that, basically, you allow for accurate predictions without manual feature engineering. You don't need to do any table flattening. There's no information loss. You have the interdependency of training examples. You can support transfer learning, and you get state-of-the-art performance. So this concludes my talk. Just again, very much like to thank the team who put the rel bench, the paper, and everything together. Here they are. And also just acknowledge all the people who are funding our group, all the amazing students, postdocs, visitors, and collaborators, and very happy to take questions. Thank you very much.
Thank you, Jure. That was an awesome talk, and I think it's amazing that you chose to share this vision at Log first as well. There are lots of questions, and I'll try my best to move through them quickly. And you can stay on as long as you like as well. So
yeah, happy to keep answering.
Awesome. Yeah. The first one is from Amir Manzoor. It's a question about the implementation of GNNs on relational data. Would you think that recursive table generation queries such as common table expressions can come in handy to create the input data?
I'm not familiar with common table expressions, but essentially my point is that you don't need any SQL queries to do this, right? All you need is to say, here are my tables, these are the columns. These columns have these types, images, text, whatever is in there, geo, and here are primary foreign key relations. And after you have defined that, the rest is pretty much automatic, right? You ingest those tables, you automatically represent them as a graph. The training table comes in, you can manually generate that. You can use the predictive query language that I showed with Kumo that generates a training table. The training table gets connected to that graph, and off you go, learning and predicting those labels. So basically the pretty much the entire process is automatic, and you don't really need the database beyond storing the data.
Yeah. The next question is from Dmitry Gavrilev. Would it be possible to design a universal GNN adapter such that it can handle multiple unrelated, possibly, databases with all the feature dimension mismatch issues and just generally issues around multiple data?
That's a great question. I think, would it be possible? I think so. Has anyone done it? Not yet. So I think it's good. I think all these feature mismatches and so on, I don't think you need to even worry about, right? Because like with the tools like PyTorch Frame, you just encode every table, every row into a message, into an embedding, and that encoding can be learned. And from there on, it's the GNN who's propagating those things, right? So if we are able, for example, to learn a GNN that's almost like agnostic from the individual column representations and can learn these column encoders that are generic, then the message passing should be able to work. So I think that's a very exciting research direction, and see how to realize it.
Nice. Yeah. the next one is from Anonymous on Zoom, and this one's almost thinking about applications in biology and molecules. And it's asking if we can integrate GNNs for molecules with tabular databases with traditional descriptors, as some physiochemical information will have an impact on biological properties. So it further asks, in the case of applying GNNs for tabular data like molecular descriptors in QSAR modeling, how can we identify the applicability domain or the confident region of this model? I think it's trying to ask, do you imagine these things being applied beyond, say, industrial use cases as well?
I mean, I would say I don't see the reason why not. I think what is also, I think, beautiful in this kind of tabular view is that it's very easy, especially in case, let's say, of biology and so on, where you want to bring in external data, external dimensions, external knowledge bases, ontologies, knowledge graphs, whatever you want to call them. You can very easily bring those additional tables in and use them for machine learning. Now, in terms of, I think this the confident region of the model. We have a paper coming up at this NeurIPS where we show how to do very reliable uncertainty estimation and quantification for GNN type models. Actually, Keshin here, this person is the first author of this research. So if you are kind of interested in kind of really having good uncertainty estimates and so on, we've just kind of published a paper about that so that you get good confidence estimates.
Great, yeah. And another question is about, I guess it asks, have you thought about applying higher order networks to tackle this task? And it's probably related to the challenges you were talking about with GNN modeling, right? This is a whole new type of data modality. So could you talk a bit about, what works well and what might be needed?
Higher order would mean in terms of like going beyond simple graphs to hypergraphs and things like that?
I think so, yes.
Yeah.
Yes.
So at Kumo, we represent the graph actually as a hypergraph. So we are a bit smarter than what I said. But yeah, I think the databases are actually not simple graphs but hypergraphs. So I think applying higher order GNNs becomes very natural and leads to better performance. So that's definitely a very good and very natural idea. I think there is, no paper has been written about this, and we need to research these things as a community to figure out what is the best approach. That's why we built the REL bench. That's why we wrote the paper. The rest is an open field. So the reason why I'm excited about this is, very few times in science or in my career, I felt like I discovered a new continent, right? And this feels like discovering a new continent, right? It's like you walk in and it's like everything is unexplored. Whichever direction you go to, you will find something very interesting. So I feel like here there is, any direction you go in, there'll be great research and great papers to publish, because it's unknown. Nobody has thought of it this way. Nobody has pushed forward this way. So I think, large scale. So as we talked about, the graph representation is a first good question. Then we talked about what's the architecture, single aggregation, multiple aggregation. How do you encode the columns? What's the architecture? Then what are good training strategies, training regimes? That's also super cool. Then with pre-training, transfer learning, multitask. That is cool. Seems like great ideas. So I think there is a lot here to kind of explore, and nicely relates to what we have been, already doing in this kind of more natural graph type of setting.
Yeah, I mean, that's really exciting to hear your excitement for this. I had one question of my own. So when it comes to just pure tabular data, right, these techniques like XGBoost were also really valuable because they were highly interpretable, right? Like you could get these feature importances and so on, and maybe even further. Do you think that feature importances and explainability would be important for some of these industrial use cases here as well?
Good question. So explainability is always an important question. And again, I didn't even put that as a future research direction, but explainability over this data is also very cool, right? Like just rethinking what does explainability mean in the context of relational tables, in the context of relational entity graphs and so on, I think again is super cool. We played with this a bit already, kind of as part of Kumo, as part of the product. Nothing too deep, but the way to think of it is like in computer vision where you have saliency maps. So a saliency map tells you your model is looking at this part of the image, your model is looking at that part of the image, and then it's up to you to say, okay, do I want it to look here or do I want it to look somewhere different? So you can imagine that you can build very similar tools that basically where a graph neural network tells you what part of the graph, what part of the tables, what columns, what rows it is focusing on. And then, if you figure out that you are predicting the probability, the churn of the user from the first name of the user, then you might be worried. But if you look at that, what the model is really focusing on is products that you purchase, their prices and things like that, the frequency and so on, you'd be like, okay, I trust that, right? So similar, basically, you can build this kind of saliency maps equivalent for this type of data.
Nice. Yeah, that makes sense. So there's a question in the chat from Lev Telyatnikov. Can I ask you to share some insights on how you might be inferring hyperedges and evaluating the meaningfulness of relations in these databases?
So, for example, the way you could create a hyperedge is that, for example, if you have tables that are kind of one-to-one, then basically you could have a hyperedge. For example, in my case, it would be user, transaction, product. That would be, for example, one hyperedge. So that would be one way to think of this. Basically, in the relational databases, they have this notion of a fact and a dimension table, and basically you can now create hyperedges by basically thinking about what tables are fact tables and which one are dimension tables. So that's one way to create hyperedges.
Ram Samarth asks, have you thought about combining graph learning on relational data with federated learning, especially for recommendation systems where maybe you might want to consider privacy concerns and so on?
That's interesting. We haven't looked into that. So I haven't, but it could be super cool, as you say, when you basically would have your data set distributed, or you would have multiple people contributing, and you would want to kind of train the model in a federated way. That would be super cool. I think it's a good question. We haven't looked into it.
And for those who are really excited to get started with this new effort, right? Is there a way to easily create a RelBench data set from existing databases? Are there tutorials or modules planned for sort of making it accessible to people in the future?
Oh, that's a great suggestion. We can consider that. And write some tutorials, but I think the best way, if it's possible, is to just reach out to us and we can help you and guide you and do this together.
Yeah. Michael Volk asks, have you considered working with graph databases as well? So triple store RDF and node graph databases like Neo4j.
Yeah, I mean, how to say, graph databases are cool, but they are not really meant for machine learning, right? So they are not optimized for GNN training. So it turns out that, for example, that if you like this, you cannot really kind of, I would say, use these systems effectively. You can use them in principle, but they become slow, expensive to run and manage, especially for machine learning GNN-based workloads. We've done some people have done some comparisons between, let's say, the Kumo, that is a dedicated kind of graph ML platform for this tabular data with its own kind of graph representation engine, versus trying to run this over a graph database. And it's 1-2 orders of magnitude difference in just kind of speed and cost and so on. So GNN, or another way to say it, right? Like, you don't run analytics queries on a transactional database, right? Transactional databases are meant for transactions, and analytical databases, data warehouses, are meant for analytical queries. And here I would say is very similar, right? Like, graph databases, triple stores are good for updates and things like that, but for any kind of analytics, ML, hard to scale.
Yeah. Marco Njegomir asks, does the inclusion of temporal information, such as the timestamps of user interactions or purchases, contribute to the recommendation system's ability to reduce redundant recommendations?
Good question. The reason, maybe let me answer this way, right? The reason why are timestamps so important, right? Maybe the easiest way to explain why timestamps are important, imagine, I don't know, like I'm a bank and I'm building a predictive model whether you will pay back a loan. Then the time when the loan was given is very, very important, because even let's say that average account balance predicts whether you will pay back the loan, that account balance has to be computed up to the time of the loan, right? Because if you know my average account balance today, then if my average account balance today is positive and I still have account with the bank, and you are trying to predict whether I paid back the loan from 5 years ago, I probably paid it back, because otherwise I wouldn't have a non-zero account balance today, right? So this notion of time and making sure you don't learn from future transactions or from future events, whatever they are, becomes very, very important. That's why the temporality is important. And similar, if you think about recommender systems, you don't want to be predicting what am I buying tomorrow from my transactions that happen a month in the future. You only want to be using, let's say, behavior transactions from the past. And this timestamp basically just more decides. These are still, I would say, in some sense, static problems. We still treat this as static predictions, right? Not trying to kind of explicitly model for temporal dynamics, even though you could and you can, but more like making sure that you always learn only from the past and never from the future, so that you don't have this time travel, information leakage, time consistency issues that many times plague machine learning systems, right? You engineer a feature offline, you put it in a model, works great. You now generate an online version of the feature. It doesn't match with the offline version. There is mismatch. That's why then the model doesn't work anymore. And you then spend months debugging this before it actually starts to work.
I think that is about it for the questions. There is another one which just popped up.
Okay.
If you have the time, of course.
I do. I'm happy to stay.
Okay. So Eran Rosenbluth says, thanks for the interesting talk. What is the reason of creating nodes of the training labels and then trying to make a prediction for these nodes, rather than trying to have a label for the user nodes and then trying to predict this label?
Good question. At the end, you can kind of fuse the training table directly to the user node. You don't have to think, oh, I have a user node and now I have a one-to-one relationship to the training table that then has the labels. Of course, you could fuse that in. That would be one example of the optimization, and that's why you would have one less hop in the GNN, right? So you don't have to do that, but conceptually the concept of the training table is very nice because that allows you to basically define the labels, and you don't have to say, oh, now you have to modify the users table. The users table can be static, but what you modify and bring in is the training table. So conceptually, kind of the concept of the training table makes a lot of sense. Now, how you implement it, you can either implement that as a separate node type with a label, or you can basically put that label directly onto the users table user node. Of course, the two would be equivalent in this case. You would actually want to put it directly onto the users table user node. But still, we wanted kind of to introduce the concept of the training table because it's natural. So that's why I explain it that way. But your insight is correct.
So there are more popping up. Tom Hutchinson asks, will GNNs, including temporal variance, take us far enough? I worry about the lack of explicit modeling about causality for predictive use cases. And I wonder if you have thoughts.
I mean, causality. Maybe two answers to this. One answer to this is that because kind of the time, because of this temporality, you can at least kind of learn in this kind of Granger causal type of way. So right, you can learn kind of how events depend on each other and how they result in certain things, right? Because stuff is time-stamped. So you can kind of order this, learn these orderings and so on. Another thing I think that becomes very interesting for this temporal data is that usually when we think of GNNs, we think of that the aggregation function has to be permutation invariant, right? We say, oh, nodes come in arbitrary order. But once you have data time-stamped, then the nodes come in a given order. They come in a time-based order. And then it's a very interesting question, for example, what kind of aggregation functions that now don't have to be invariant to the permutation, they should actually account the ordering, they should account the permutation, should we develop? Going back to my notion of what is the GNN architecture. So that's another, I think, very interesting question, especially for these time-stamped nodes. How do we aggregate them?
Yeah. So there are more. Ram Samarth asks, is this one method where we can bring in concepts such as neural algorithmic reasoning for relational operations? And I was thinking along similar lines, right? Like, what if my queries are on sets of nodes, or I want as output, say, sequence of nodes or subgraphs? Like,
that is a super cool question. We haven't thought, like, very honestly, we haven't thought that far, right? It's clear how to do node level predictions, how to do link level predictions, and I think it's super cool to take this notion of algorithmic reasoning and say, okay, what if I want my prediction objects to be much more complex in terms of sequences, subgraphs, and things like that, as you were saying. That would be super cool to generalize it to that and kind of to interpret it in this language of, let's say, databases, tables, and say, okay, these are the natural use cases for this. I think that would be super, super cool.
Nice, yeah. And I suppose another thought type question is from Nikos Kanakaris. Do you think we could combine data from relational databases like MySQL along with unstructured NoSQL data like MongoDB, or I mean, even just piles of text from the internet, right? Language models and so on.
Yeah, I mean, maybe a few things to say here, right? Like relational kind of databases, definitely. If you have data stored in JSON, that's a graph as well, right? Every JSON is a tree, and now you can kind of superimpose and connect these trees if you like, right? So you don't have to have this kind of schema. You can be schemaless, and everything still works. Now, let's say text data, images, they can very easily, nicely be stored in the columns, and you just have a more complex encoder that encodes the text, encodes the image that is in the column, and you could back propagate through the GNN all the way down to the encoder, to the CNN or whatever vision transformer that you're using to encode the given image. So you can definitely do that. Now, of course, you could ask, okay, how does this relate to the LLM stuff, right? And I would say the following, right? LLMs are amazing, but these are big, giant, generic models trained over public data. But a lot of, if you think about business use cases and also real world, kind of just general real world use cases, is that every organization has their own data, and they have their own tasks, their own procedures, their own labels, and they want to maintain that specificity and that uniqueness that makes them different from everyone else, right? So there will always be need for task-specific AI models, right? Today we have LLMs as a kind of generic, non-task specific model, but at the end you will have a lot of task-specific models that need to be built. Now, how would you build a task-specific model? One way is to say, let me bring the let's say all the tabular data and train a GNN that, let's say, predicts whether a transaction is fraudulent. Or you could say, let me now take all the transactions of a given person, let me textify all that, give user trajectories of 7 people as a part of the prompt to an LLM, and now give it 10,000 transactions of the person in question right now, and the last transaction, and ask the LLM whether this transaction was fraudulent or not, right? And maybe you can do this only over transactions, but now what if you also want to include the payment data, and you want to include what offices that person went to, and you want to include the address information and things like that, right? So I think my point is that these things are very nicely complementary to the large language foundation models. I think foundation models are great at understanding natural language. They are great at kind of this kind of human level communication and reasoning, but there is huge need for task specific models that get trained to solve a given task really, really well. And we've been doing some benchmarks internally. There's a huge gap of, how much can an in-context LLM model predict versus how much can a neural network that was trained to spot a given type of fraud or to predict a risk of, patient having some kind of complication. There's a huge difference between the two. So there will always be need for this.
Yeah, that was really fascinating. I think it's great that we're getting to pick your brain for all these things. And I'll ask one last question. And this is about, do you envision a role for quantum algorithms in accelerating relational and graph machine learning? Do you think quantum computing might impact efficiency and scale? And perhaps more on the near term, like, do you think new hardware is needed for graph ML generally?
Good question. How to say, I think quantum is awesome and it's going to impact everything. So I think it's going to impact GNNs as well. One thing I would say, I think but you're asking about the new hardware. I think, training GNNs, I would say, is an order of magnitude harder than training LLMs or anything else, right? Because, and why is it harder? The problem is because the data is not IID, right? Everywhere else, you kind of can just flood the data through. But in graphs, you have this connected structure, and you cannot partition cut this connected structure in any good way. So, for example, the barrier to entry is much, much larger. And that's, I think, why you also see, for example, in industry, there's been a couple of companies who were able to really invest and build their own GNN platforms, right? I built one at Pinterest. It took us 4 years to build it. There's tens of millions of dollars of investment, but it really worked, and it totally transformed Pinterest. It led to 30-50% improvement across a number of different metrics, right? And if you follow, for example, what Amazon is doing today, they are able to harness GNNs everywhere to great success. But there is only a small number, I would say, of organizations that are able to attract the talent to build systems that are scalable and can learn GNNs at scale. So I think there is a big need to either do something in the open source. We've been pushing kind of PyG forward as much as possible, so that we can start building bigger and bigger models and bigger networks. And I think new hardware will be very, very important here, right? At Kumo, for example, our compute cluster basically has 3 types of machines. It has large memory machines to store the graph. It has machines with SSDs to store the column information, to store basically the node attributes, and it has GPUs to train the models. And that's very, very hard, right? And now saying, okay, what if I have to distribute the GNN across multiple machines, multiple GPUs, and things like that? It gets even trickier. So I would say these are very hard problems that we need to figure out how to solve to really realize the true power of GNNs.
Great. I think that's a really nice note to end this then. Thank you, Jure, for all your time, and thanks everyone for engaging so much with this keynote as well. I think it went really well, and yeah, I think it feels like the birth of a new field. So it's going to be really exciting in the coming months.
Yeah, thank you so much for having me. Really enjoyed all the questions. It's great to interact with you. Please let me know if you have any more questions, or if there is anything else, drop us an email. If you have any feedback on the Rel bench, or you'd like to contribute, also reach out to us. But thank you again for having me. It was great to interact with you all, and have a good rest of the day and the rest of the conference.
Thank you. Yeah. And for the rest of the conference, right? Next, we have these poster sessions on GatherTown. And these have already started. So, all the links are in our Slack channel as well as our website. And I encourage all of you to hop on to GatherTown and interact with all the awesome posters we have. We have a range of things from theory to foundational topics in GraphML, as well as applications to cool new areas. And I think with that, once we have the poster session, after that, we have a few orals as well today. So I definitely recommend all of you to tune in for the orals as well. I think today is going to be really interesting to discuss some methodology questions as well as some benchmarking questions in the oral presentations. So looking forward to all that, and looking forward to all of your participation at LOG. And thank you very much on behalf of all the organizers for tuning in and for engaging so much with the conference. And I think also for all the local meetups, it's really awesome, I think, that these things are happening. So yeah, thanks a lot. And I'll be signing off with that.
Okay. Hi, Xinyi. Hi, you're still muted.
Oh, sorry, I didn't notice that.
Is that how I pronounce your name? Xinyi.
Yeah, it's pretty accurate.
Okay, then let us go with that. Yeah, thank you for presenting your poster here in your paper. I think it got its share of attention already, and we want to make sure it gets its other fair share here. All right. Do you maybe already want to try sharing your screen?
Yeah, sure. Let me do that. No.
Good.
You see the screen?
Yep, we see a
Okay.
nice zoom. Okay, then let me also pull up my notes. Where are my notes? Yeah, and we hope that the Friends of the Sun now soon starts aggregating here and leaving the poster session, and we switch back over here. Yan Chao, are you here? No, I think that's a no. Oh, Chaitanya is here. Admit. And there's Chaitanya. Chaitanya, do we have to admit every person manually here?
Hey, Hannes, were you saying something? I just joined.
Yes. Do we have to admit every person manually to this meeting?
So unfortunately, that's what it seems like. Unless like the people who are managing it go and change to admit everyone, in which case, as you know, we could get like Zoom bombings and stuff. I don't know what's the best way to do this.
Okay, then can someone stay with me here while I'm doing the things and the talkings and press admits a few times?
Yeah, I'm around.
Ali, do you want to support us in that as well? And I will make you a co-host. Okay. Good. But I think then we have reached the mark of the hour, and we are 1 minute past the mark of the hour and can get to our oral sessions. So, Friends of the Sun, welcome back from some nice posters that I hope you saw and maybe found some inspiration, and you're coming here to the right place to get some more inspiration and find out about more cool papers. So yeah, for doing that, I want to hand over to our first oral session of this whole conference by Xinyi about her way to demystify oversmoothing in attention-based graph neural networks. Okay, then let's go.
Hello, everyone. I'm Xinyi, and today I'm going to talk about oversmoothing in attention-based graph neural networks, including our well-beloved transformers. And this is a joint work with my wonderful collaborators, Amir, Zihui, and my advisor, Ali. So message passing GNNs and transformers, where the latter can be viewed as message passing GNNs on complete graphs, are known to suffer from increasing depths. In fact, for message passing GNNs, the optimal depth is usually 2 to 5 layers. And for transformers like BERT, the optimal depth is usually 12 to 48 layers. But nonetheless, both are relatively shallow compared to convolutional neural networks. So this is because both of them suffer from the phenomenon called oversmoothing, which refers to the case where increasing depth leads to homogeneous node or token representations. And then the bottom is a visualization of the output of each layer in a 5-layer GCN. And we see that as we increase from 1 layer to 5 layer, the node embeddings converge to roughly the same representation vector. So oversmoothing has been considered as one of the major challenges for developing more powerful GNNs. And people are curious about like what is the underlying mechanism leads to this phenomena. And what has been understood in the literature is the simplest case, where we have symmetric graph convolutions with activation functions being ReLU and leaky ReLU. In that case, it has been rigorously proven that oversmoothing would happen exponentially, meaning the architecture loses representation power exponentially with respect to model depth. The intuition is actually quite simple for the graph convolutional case, because one can think of what graph convolution does to each node in each layer is that it updates the root node's representation with the average of its neighboring nodes. And this operation would smooth the node representation over the entire graph. And if one applies too many rounds of this operation, all the node representations over the graph would converge. Attention, on the other hand, was introduced precisely because people want to distinguish neighboring nodes in the update and only do the update with important neighbors. So the natural question arises is, can attention prevent oversmoothing? This, in fact, is a long-standing open question in the literature. On the one hand, some people believe that attention can learn the right or appropriate aggregation to fundamentally alleviate or prevent oversmoothing from happening. On the other hand, people empirically observe that it seems inevitable for attention-based GNNs such as GAT or transformers oversmoothing also seems inevitable for attention-based GNNs such as GAT or transformers. So in this work, so here's the spoiler. So in this work, we provide a definitive but negative answer to this long-standing open question. So then the second question we investigate in this work is that what is the role of nonlinearities on oversmoothing? Can we conclude about a general class of nonlinearities instead of the specific instances of ReLU and leaky ReLU? Because, for example, both of them are homogeneous, and it is hard to tell whether that's a key property leads to oversmoothing. So here's the main result, and then the punchline is attention-based GNNs under general nonlinearities also suffers from oversmoothing exponentially. And under our realistic and general assumptions, our analysis is able to account for a general family of attention-based GNNs, including popular architectures such as non-symmetric GCN, GAT, GATV2 transformers, graph transformers, and different variants of them. Moreover, our analysis is also able to account for most common nonlinearities such as ReLU, leaky ReLU, 10H, eLU, and even non-monotone ones like GLU or CLU, where GLU is a nonlinearity deployed in GPT. Our analysis also reviews that although oversmoothing happens exponentially for both graph convolutions and graph attention, it is potentially at a slower rate in attention-based GNNs compared to graph convolutions. And then the specific rate would depend on which nonlinearities one uses. So here, let's dive into the mathematical analysis of our main result. So by graph attention, I mean that given a node representation vector HI and HJ for node I and node J, we first use the attention function psi to compute the row attention score between node I and node J. And then we perform a mass normalized attention based on the graph structure in the sense that for each node I, we only compute the normalized attention score among its neighbors using the softmax operation. And doing that, we can arrive at the layer-wise update rule, where the output of the t+1 layer would be the product of PT, representing the aggregation operation of layer T, and layer t+1, and then the input to that layer, and then the weight of that layer, and then pass through the whole product through the element-wise nonlinearity function sigma. And then for oversmoothing, we follow the definition of the literature, where we first need a no similarity measure mu satisfies the condition where it equals to 0 if and only if all nodes have the same representation vector. And oversmoothing is defined to be the case that mu converges to 0 exponentially with respect to the model depth. And then later we will see that since oversmoothing is concerned with the behavior of xt as t goes to infinity, and as we abstract the underlying GN as a dynamical system, we're basically interested in the ergodicity behavior of the underlying dynamical system. And then in this work, we use the following no similarity measure, where it measures the norm of the distance to the norm of the distance of the node embedding to the O1 space. But I want to remark that our result directly generalized to any Lipschitz no similarity measure, including the popular one using the literature, such as the Dirichlet energy. But the one we use is easier to deal with in the proof. And then, of course, we adopt some assumptions in our analysis, which is actually quite minimal. First, we require the graph to be connected and non-bipartite. And second, we require the raw attention function to output bounded attention score for bounded input. And then we require the weights to satisfy certain regularity condition. And lastly, we want the nonlinearity to be non-expansive in certain sense. And then to satisfy the last assumption, one way is to require the nonlinearity to be one Lipschitz and has 0 as a fixed point. And then, as I said, so the way we look at GN is to abstract it as a dynamical system. So recall the layer-wise update rule. If the nonlinear activation functions are identity map, then the output of the T+1 layer could be written as this product of P matrices, and then the input to the network X, and then the weight matrices Ws. And note that due to attention, the aggregation matrices are different for different layers. And then this is precisely one of the main technical difficulty in analyze attention-based GNs, because previously to analyze oversmoothing in graph convolutional networks, one can just do a spectral decomposition of a single matrix. However, here, because different layers have different aggregation matrices due to attention, such analysis technique will not work anymore. And we need to resort to some other tools. But before I show you how we can deal with the inhomogeneous matrices across different layers, let me show you how we deal with the nonlinearities. So the way we deal with nonlinearities is to make use of the following mathematical trick, that the application of layer-wise activation function to a vector could be written as a diagonal matrix. And hence the ith column of the node embedding could be written as a weighted sum of product of matrices Ds and Ps, where Ds representing the nonlinearities, Ps representing the aggregation matrices. And then under our assumptions on the nonlinearities, the diagonal matrices representing the nonlinearities would satisfy the following condition, where the entries will be between 0 and 1. And then we prove the following key lemma, which states that under our assumptions, the graph attention mechanism, despite being able to generate different aggregation matrices for different layers, it cannot fundamentally change the connectivity pattern of the graph. Although this result may seem a little bit weak at the first glance, this is actually the key result leading to the exponential oversmoothing result. And lastly, recall I said that because for oversmoothing, we're interested in the behavior of xt as t goes to infinity, and in the language of dynamical system, we're interested in the ergodicity behavior of the underlying dynamical system. And here in our work, we define ergodicity to be the case where the product of matrices converge to the situation where all rows of the matrices are equivalent, and that exactly corresponds to the requirement for the oversmoothing. And recall the ith column of the node embedding can be written as the weighted sum of the products of Ds and Ps. And then if we define the family of matrices DPs to be M, then we show that any sequences of matrices DCMPs will be ergodic, meaning that the infinite product of them would converge to the case where all rows are equivalent, which basically means that they would oversmooth. However, to quantify the oversmoothing rate, we need to get the exponential convergence rate. And then to do that, we need another notion called the joint spectral radius, which is a generalization of the notion spectral radius for a single matrix to a family of matrices, which measure. So basically, joint spectral radius measures the maximum growth of a product of an infinite product of matrices from this family. And recall that basically oversmoothing is defined to be the case where the rows of the node embeddings converge to equivalent rows at the exponential rate. It basically is equivalent to say that the node embeddings, when we project it to the space perpendicular to the O1 space, it vanishes at the exponential rate. So if we define the family of matrices dp, when we project them into the space perpendicular to O1s, we get this new family of matrices M tilde. And then under our assumptions, we can prove that M tilde is strictly less than 1, meaning that the family of product of matrices dp's, when we project them into the space perpendicular to O1, it will vanishes exponentially because the joint spectral radius is less than 1. So putting everything together, we arrived at our final result. Basically, it says that under our assumptions, oversmoothing would happen exponentially for attention-based GNs, and then the convergence rate would be determined by the joint spectral radius of the family of matrices Ds and Ps, where Ds are determined by the nonlinearities, Ps are computed by the attention mechanism. Although the joint spectral radius for a family of matrices is in general very hard to compute, it is straightforward to lower bound it. If we let lambda to be the second largest eigenvalue of the graph convolution, then under our assumption, it holds that the lambda will lower bound the joint spectral radius, which determines the oversmoothing rate for attention-based GNs. And then from the previous literature, we know that graph convolution, the convergence bound for the graph convolution case is upper bounded by lambda to the power of t. It is thus natural to expect that even though both attention-based GNs and graph convolution suffer from exponential oversmoothing, attention-based GNs potentially have a better representation power at the finite depths because the upper bound is looser. And then we verify our result in both homophily benchmarks and also heterophilic benchmarks. And in both cases, we see that attention-based GNs and suffer from exponential oversmoothing, but the oversmoothing rate would be slower than graph convolution, and also the specific rate would depend on which nonlinearity function one chooses. And that is because we know that the convergence rate depends on the joint spectral radius of the family of matrices Ds and Ps, and nonlinearities determines the matrix D, and different D would give you different joint spectral radius, and which implies that different nonlinearities would give you different oversmoothing rate. And we also see that ReLU, despite being the default choice for GNs, it actually oversmoothes faster than, say, leaky ReLU. So one lesson I want to say about that we learn from this set of experiment is that usually people in the literature, when people deal with like oversmoothing, they would resort to some very dramatic solutions like residual connections, normalizing layers, or even like gated gradients. But maybe like before going to those like like dramatic like solutions, maybe the first thing you want to try is just to simply switch to a different nonlinearities, and that might already give you a better GNs that is more robust to increasing depths. So let me conclude my talk here. So in this talk, and also in this work, we have answered two fundamental open questions about oversmoothing in attention-based GNs. The first one is, can attention prevent oversmoothing? And then the answer is no, since graph attention cannot fundamentally change the graph structure, which in fact leads to oversmoothing at an exponential rate. And second, what is the role of nonlinearities on oversmoothing? There's nothing special about like ReLU and leaky ReLU. Despite both of them being homogeneous, oversmoothing is a problem for a wide range of nonlinearities, including non-monotone ones like CLU or GLU. And then the specific oversmoothing rate will depend on which nonlinearity function one chooses. Yeah. Last but not least, here concludes my talk. Thank you for your attention.
Thank you, Tinyi. This is marvelous. I really like how you have your nice theory, but in the end, right, we actually get some additional nice practical recommendations out of it. And yeah, this is probably not only interesting, it's also very insightful in practice, I think. Yeah, and
thank you.
With that, I wanted to maybe have one last little question from my side, just as because we have a minute. Yeah, what do you think is now like? We have all these over-smoothing answers and questions, and do you now think it's worth to further work on over-smoothing, or do you yourself want to further work on over-smoothing, or do you think maybe other fields are more interesting after we've, as a community, invested so much time in this question now already?
Yeah, I think over-smoothing, like in my opinion, so it becomes an important question in the literature, implicitly because people have this assumption that when you have a bigger GN, it means that you have for each node you have a wider range of information, so that should give you a better result. But then I think over-smoothing, in my opinion, would be a problem if your task indeed need a long-range interaction, right? Because it means that this model is not able to aggregate long-range long-range information. However, if your model, say, if you just want to do like, if you have a very strongly homophily graph, meaning that you only need like one or two hop of aggregation. So maybe in that case, like a shallow architecture would suffice. I think that's my take on the question. But I think the problem is like, say, but there's like gigantic, like, I guess, network data set where the diameter of the graph is like very, very big. And in that case, we would need like very like deep architecture in order to I guess to perform better on the task. So I think the answer would be definitely task and data dependent.
Okay, then marvelous answer once more, and thank you for the information and the nice presentation. With that, I would switch over to our next presenter, and that would be Nasser. Nasser, do you want to try sharing your screen and unmuting and turning on your camera to maybe present your paper here? And to all the other folks in the call, I'm sure our speakers would be delighted to see your faces if you folks want to turn on your cameras. And yeah, that's, for me, I think it at least makes the things always much more much more relaxed. Yeah. Okay, but then Nasser, are you here? Can we hear you?
Yes. Hi, Hans. Can you hear me?
Yes, perfect.
Perfect.
You want to try sharing your screen?
Sure thing. I'll just start.
Oh, and Chaitanya made a great point. Chinyi, if you can answer some questions in the Slack, that would be very much appreciated as well. Good.
Right.
And then-
Everyone can see my screen, right?
Yes, yes, it looks beautiful. And with that, do you maybe yourself want to give a very quick introduction to yourself, and then let's get into your paper?
Sure. So my name is Nasser, and the second co-author on our paper, Luke Dickens, is a professor of machine learning at University College London. So to give a brief overview about myself, so I studied mathematical economics as a bachelor's degree at University College London, and then did a master's in information and data science at UCL. So as part of my master's thesis, I developed a theory on dynamic hypergraphs and dynamic hypergraph regularized non-negative matrix factorization together with Professor Luke Dickens. And essentially after my master's degree, I have been aiming to implement the algorithms that I sort of theoretically formulated on real-world data sets, and I have been able to present it to you guys today at the conference. So let me begin. So first of all, I would like to thank the organizers, the program chairs, the reviewers for their comments and their feedback, and for creating such a wonderful conference for all researchers from all across the world to present their findings. So I won't take much time and I'll just begin. So our research is basically on dynamic hypergraph regularized NMF models. So essentially, so the structure of the presentation will be as follows. We'll first introduce, I'll give you an overview regarding the different models in dynamic hypergraph regularized NMF algorithms. We're going to provide a motivating example that is basically sort of provides us that level of grounding for why we wish to study dynamic hypergraphs and dynamic hypergraph NMF models. And next, we'll show, using certain definitions, we've formulated a derivation of the update rules as part of a dynamic hypergraph NMF implementation. Next, we'll define the data sets on which we implemented our algorithms and the results from the different implementations that we did. And finally, we'll be stating some concluding points and future work that we plan on doing on the basis of the theory and applications we state. So first of all, hypergraphs, as we know, are a powerful way to represent and reason about data, since essentially they capture higher order relationships between nodes, and these representations lead to more expressive models that can capture much higher order correlations than unigraphs can do. There exist numerous pre-existing data sets that can be readily represented as hypergraphs, and a number of applications already do exploit this capability, such as image retrieval, recommendation systems, link prediction in social networks, etc. Recent advances in dynamic unigraph methods, essentially what they do is they make predictions about links between nodes at the current time based on previous observations. Synthesizing these two strands of work, we present a modeling framework for dynamic hypergraphs, an algorithm for one step ahead prediction of the dynamic adjacency matrix, and essentially experiments that demonstrate the improved accuracy of this algorithm compared to more conventional approaches. Now, the motivating example. So let's consider a data set of supermarket baskets where each is a collection of products bought together. So essentially, this can be captured by a hypergraph where each product is a node and each basket is a hyperedge. Most simply, a hyperedge would be a set of nodes, and here an intersection of hyperedges would indicate products that are common to the corresponding baskets. If we were to reduce this to a unigraph of products, such that two products share an edge, if they share a basket, we would lose some of this information. If time information is given for baskets, these baskets can be readily modeled as a dynamic hypergraph where we partition shopping baskets by time period, which can be months, years, or even more granular, such as weeks or days, where each period is captured by a hypergraph to analyze how product choices change over time. Next, looking at the contributions of our research. So essentially, we have identified the research gap by synthesizing the fields of dynamic unigraph methods and hypergraph formulations of data to present a modeling framework for dynamic hypergraphs. We have defined the new paradigm of dynamic hypergraph regularized non-negative matrix factorization by defining concepts related to dynamic hypergraphs and an objective function which incorporates regularization based on the time series of hyperlaplacians, which is basically the hypergraph version of Laplacians. And if you're aware of graph theory, that in hypergraph theory, the Laplacians are not necessarily the difference between the degree matrix and the adjacency matrix, and that on the basis of the Laplace operator, you may have different definitions of Laplacians. Hence, it's important for us to segment out between hyperlaplacians and Laplacians. But in my presentation, I would be using them somewhat interchangeably because my work is usually around on normalized Laplacians. And then we developed two algorithms for one-step ahead prediction of the dynamic adjacency matrix called DY-HGR-NMF, which is an asymmetric version, and SDY-HGR-NMF, which is a symmetric version, for optimizing the loss function of interest. We evaluate these across a number of data sets, and these algorithms are compared with a selection of baselines, where we see that DY-HGR-NMF outperforms all other models. So let's get to the theory now. So essentially, a discrete dynamic hypergraph, we define this to be a time index set where G subscript T is a triple, where capital V is the set of nodes, ET is the set of hyperedges, and WT is a diagonal matrix with non-zero entries. The hyperedge set has cardinality M subscript T, so we allow hyperedges to vary in their cardinality across time. And E small e subscript I comma T is an NIT ordered tuple. So essentially, definition 2, what this does is that it allows us to define the adjacency matrix to be the following. If you look at hypergraph literature, some people choose to define the adjacency matrix to be HTWT times the inverse of the degree matrix for hyperedges times HD transposed minus the degree matrix for nodes. But that is simply a modeling choice, and whether you choose one or the other depends on certain restrictive requirements. But we choose to go with the former. And at time t, the hyperlaplacian, or the Laplacian for brevity, is defined to be in this following unnormalized version. So essentially, in our paper, we have extended the concepts of incidence, node degree, edge degree, and adjacency matrices to the time-dependent domain. Given this G star graph, or set of hypergraphs, we aim to predict the properties of G subscript capital T plus 1. This problem can be caused in a number of ways, but in our paper, we essentially aim to predict the adjacency matrix at capital T plus 1 time. Now we can essentially model how we want to predict this adjacency matrix as an approximation of the product of the basis matrix at time capital T times the feature matrix at time capital T. For parsimonious arguments, we have essentially chosen to state the basis and the feature matrices as at time capital T as just BNF, but they are essentially assumed to be at time capital T. So essentially, you can see from the formulation of the objective function and the optimization problem that we have stated is that this aims to model the effect of encouraging two nodes, nu I and nu j, arbitrary choice, to be embedded close to one another. You can see from the term, which is the explicit regularization, which is the trace term, that this can be intuitively thought of as the difference between the ith column vector of the feature matrix and the jth column vector of the feature matrix, square these two, and essentially sum across all k column vectors of the feature matrix. And essentially, this term would be small if we share hyperedges in the previous time steps, with a greater emphasis on recency, as you can see from the theta term, as it's autoregressive in the formulation we state. Now, to basically derive the update rules, to make this approximation, we begin by an arbitrary initialization of the basis matrix and feature matrix, and essentially we iteratively update elements of these with the following provided update rules. And given the objective function, we derive these update rules using a so-called alternating least squares methodology, where we establish the Lagrangian of our objective function, and essentially we take the first order conditions and use alternating least squares to derive these update rules, where essentially what you do is you fix one variable and you take the first order derivative with respect to the other, and vice versa. Next, we get to the evaluations that we perform. So what we do is that we have applied these to the following three data sets. So the co-authorship and email data sets are temporal, higher order network data sets, where a sequence of timestamp simplices is modeled, and each simplex is a set of nodes. For the co-authorship data set, the nodes are the authors, and a simplex is a publication recorded. For the email data set, the nodes are the email addresses at Enron, and the simplex is consisting of a sender and all recipients of the email. Now for the stocks data set, this is a novel data set that has been derived from adjusted closing prices of the top 9 blue chip stocks from 16th of December 2020 to the 16th of December 2022. These have been processed to give a dynamic hypergraph. Hyperedges in this dynamic hypergraph indicate stocks that are jointly correlated with each other with correlation measure of at least some arbitrary C, which we select. Now, getting to the results, we compare our two algorithms, DY-HGRNMF and SDY-HGRNMF, with baselines 8GRNMF-T, S8GRNMF-T, which are the asymmetric and symmetric versions of the so-called GRNMF algorithm postulated in March 2018. The regularizer in HGRNMF-T and S8GRNMF-T is just the Laplacian at time cap t-1. So in them, we do not take the sequence of Laplacians or thetas in an autoregressive manner into account. We postulate two other simple baselines, a matrix version of martingale prediction, which is basically prediction of the adjacency matrix from the previous matrix, and a so-called collapsed tensor method, where we predict the adjacency matrix as the mean adjacency matrix from previous time steps. So essentially, these two tables of results, they show the root mean squared error over time for the proposed models and baselines. All hyperparameters have been optimized by grid search over feasible values. For each NMF method, hyperparameters include feature dimension cap K, which is the number of rows of the feature matrix, regularization strength lambda, the number of outer iterations of the algorithm, which is set to maximum of 3, and the dynamic hypergraph methods have an additional parameter theta, which, as you saw in the objective function in definition 3, is a geometric weighting parameter. And we can see from these two tables that our algorithm DY-HGRNMF outperforms all others. So essentially, in our research, we have presented a new framework for modeling dynamic hypergraphs and present new models for approximating adjacency matrices from past observations. Evaluations show that our asymmetric model predicts adjacency matrices more accurately than a competitive baseline HGR-NMF-T that does not integrate the entire history of observation. For future work, we aim to go towards two promising methodological directions. First of all, we aim to look into methods to predict missing nodes from partial hyperedges, which would basically be looking at link prediction beyond binary relationships. And lastly, look at methods to predict incidence matrices, which would be looking at higher order groupings of nodes beyond pairwise associations. So thank you very much for attending, and I would like to open the floor for any questions. I believe there's not much time left, but if there's any question that the audience may have.
Not much time left, but yes, thank you for the nice presentation, Nasser. And a little question. So I'm not in this field, right? And how ripe is this, like hypergraphs and using hypergraphs? Is this already something very typical and people in industry are doing it? Or is this more like sort of a researchy area right now and not used so much?
That's a really good question. So if you look at the references, I think the best thing to do would be to look at the references that I quote. So these two references by Austin, essentially what Austin did in his research in hypergraphs at Cornell was that he looked into the concept of cyclical closures to essentially predict higher order links, right? So this was him looking at hypergraphs, and this was about, as you can see from the data, this is 2018. And more recently, Gao et al.'s papers, so he basically published one paper related to hypergraph methods and practices, which was back in 2020. And I believe he's done some more work on certain specialized hypergraph learning methods based on that seminal paper back in 2020. Because essentially what the 2020 paper does is that it just states a set of hypergraph learning methods that, for example, they first looked at one tensor learning methodology, and then they looked at some levels of clustering and classification methods too. As in my framework, you were essentially just predicting the adjacency matrix. But as I previously said, essentially given a sequence of graphs, you have to predict one step ahead, but that prediction problem can be formulated in a number of ways apart from predicting the adjacency matrix. So Gao looks at all of those different methods, and there have been some subsequent things that have been done. So there's a lot of development taking place. There are some applications that you can see on different data sets over the past few years as well. I could go on about this, but essentially it's a rapidly growing field, and I would expect there to be more things in the future.
Okay, then if there's more interest, like from my side, regarding this as well, and I'm sure people can feel free to reach out. And with that, I would like to say a very last thanks to you and hand over to the next speaker. Jan, do you want to try out your screen share and if we can hear you well?
Yes, let me try. Can you hear me?
Yes, that seems perfect.
Okay.
Good. And we can see the screen. Ideal. Okay, then let's keep the questions coming, friends of the sun. If you have any, then just shoot them into the Slack and we'll cover them here. And with that, Jan, who are you and what are you presenting here today?
Hi, yes, I'm Jan. It's my honor to speak here today at LOG 2023. I'm a PhD student from RWTH Aachen, and it's my honor to present a reproducibility study on the long-range graph benchmark, which is joint work with my colleagues Martin Ritzert and Iran Rosenblut, as well as my supervisor Martin Jure. Yes, so let's jump right in. Actually, message passing GNNs are of course famously known to be local architectures. So every GNN layer only allows interaction between vertices that are immediately adjacent. And since the inception, this has led to concerns whether or not such message passing GNNs are able to propagate information across long distances, which is also well known under the term long range interactions. Of course, a common concern here is that this may be a performance bottleneck of message passing GNNs, which may or may not be good enough at this sort of long-range interactions on some tasks that may have a strong semantic dependence on such interactions. Now, as I said, this is not a new idea. In fact, Gilmer et al. 2017 already proposed this as a potential bottleneck and proposed virtual nodes as a solution for this. But very recently, there's been an uptick of interest in this with the rise of graph transformers, which have become immensely popular over the last few years. And a core motivation of those techniques is, of course, their ability to perform long-range interactions through self-attention mechanisms that are built into the graph learning pipeline. So one of the core claims of graph transformers is that they are inherently better at facilitating long-range interactions. And in order to evaluate these claims, of course, a core interest of research has been the search for real-world tasks that do indeed depend so strongly on long-range interactions that they can be used as benchmark data sets to measure how whether or not these new architectures are actually significantly better at learning to exploit such long-range interactions on those tasks. So one by now very well-known collection of such data sets is the long-range graph benchmark proposed last year at NeurIPS, also known as LRGB. And this is a collection of 5 learning tasks which are strongly conjectured to depend on long-range interactions and such that architectures able to exploit such interactions more effectively will end up performing better on those tasks. The main logic behind this is that these graphs have a size and radius larger than comparable prior benchmark data sets, and they're also trying to learn tasks that somehow semantically depend on long-range interactions. So here's a brief overview over them. So although you've probably seen these before, there are 2 graph level tasks, peptides func and peptide struct, both of which operate on molecular graphs which model peptides. And this is a graph level classification and regression task respectively. Then there are 2 node level tasks which model semantic segmentation of images as a node classification task on superpixel graphs. And finally, there is a link prediction task that tries to predict, given the 2D structure of a molecule, tries to predict pairs of vertices that will be close to each other in the simulated 3D structure of the same molecule, even though they're not immediately adjacent to one another in the original 2D graph. So these are the data sets, and the initial performance reported on them indicated a strong performance advantage towards existing graph transformer architectures, which was seen as confirmation that indeed these tasks do depend strongly on long-range interactions, and that those graph transformers are indeed better at utilizing such long-range interactions than existing message passing GNNs. And subsequently, this set of benchmark datasets became immensely popular in the graph transformer literature, as well as other graph learning approaches trying to evaluate long-range interaction, and has been cited many times since. And the common purpose of these is usually to demonstrate that a new architecture is able to facilitate long-range interactions to a degree not achievable by message passing GNNs on the same data sets. Now, the main point of our work here is to evaluate whether or not these performance margins are accurate. And the main claim here is not that the graph transformers are worse than what they are reported to be, but rather that the baseline values for the GNNs are actually needlessly pessimistic, and that GNNs themselves can perform much better on these tasks than what is reported, thereby raising questions of whether or not these tasks can actually be used to measure how good an architecture is at exploiting long-range interactions. So the common denominator, that's our main concern here, are the hyperparameters, which we found to generally be suboptimal to the point where they give us substantial disadvantage to the message passing GNNs and skewing the results. So what we did is we took the 4 architectures already shown here, so GINE, GCN, gated GCN, and GPS, for which there are already existing results reported in the literature. And we basically retune all 4 of them on these 5 datasets. With these fairly moderate hyperparameter budgets, and what we find is that results can improve massively already just by doing this. Now, I have said here that tuning hyperparameter is what we need. It's not all we need, because there are some additional confounding factors where we discovered on some of the datasets, but suboptimal hyperparameters certainly were the common denominator of what we observed. Two things I want to point out briefly is that we do tune the usage of Laplacian positional encoding and random walk structural encodings for all methods, including all message passing GNNs, because in the end, this is just a hyperparameter, and we can always use these additional node features for all learning architectures, not just transformers. The other thing I like to point to is the depth of the predictive head, which we found to be the deciding factor on the peptides datasets in particular. So tuning this away from the linear prediction head that was consistently used in the literature really changed the picture of how well the architectures perform on those datasets. So this is what we want to start with. This is our ablation study for exactly this hyperparameter on the peptides datasets. Maybe let's first have a look on the left-hand side where we evaluate peptide struct with our new hyperparameter budgets. So the first thing I want to point out are the blue bars. These are the original results from the literature, which all use one-layer prediction heads. So linear prediction heads applied to the graph level embedding obtained after pooling. And here we see this large performance margin that was originally reported, where GPS has a wildly lower mean absolute error than the message passing baselines. The orange bars represents an ablation study where we didn't tune the hyperparameters at all. All we did was change the depth of this predictive head to 2. So now there's one hidden layer in there with ReLU activation, and we have a deep feed-forward network that performs the classification after pooling. And this actually has a massive effect on this data set. So we see that the large margin observed with the linear prediction head completely disappears. GPS is still slightly better than the GNNs, but it really is a marginal improvement, not a massive one. And then in green, we have the fully tuned results. So we actually tune the parameters with the budgets we just specified. And now we actually see, interestingly enough, that the GNNs are slightly better than GPS. And while the error bars are not shown here, the difference here is significant. So here GCN and the other message passing GNNs actually outperform GPS after tuning. So this raises serious questions of whether or not GPS actually exploits long-range interactions on the stars better than the GNNs, or whether or not this is even necessary to perform well on this task. On peptides function, the picture is similar, although slightly different. When we only switch the two to a 2-layer predictive head, we do see a significant improvement, although not quite as extreme as for the other data set. But after fully tuning the hyperparameter budgets we specified, we do actually see an improvement of all message passing GNNs to the point of outperforming GPS. Interestingly enough, the performance of GPS actually worsened by choosing a deeper predictive head, although the original performance was recovered by tuning the remaining hyperparameters, but still the message passing GNNs actually outperform the graph transformer here. So what does this result show us about these specific data sets? It does seem like the prediction target does somehow depend in a nonlinear way on global graph statistics, which is something that a message passing GNN would only be able to capture if we have a deep predictive head after pooling. A graph transformer may not be subject to this problem when using a linear head because it can already process those global graph statistics in each layer with its feed-forward network. So this seems like a reasonable hypothesis as to what we're observing here, explaining these shifts in performance. Okay, so this is the tabular version of the same data. Here you have the old results above, below our new results, and below this you have some additional results reported on those data sets in the follow-up literature. Now on peptides function, there's actually improved results reported that outperform GPS that are still better than the best results we were able to obtain with message passing GNNs. But the overall gap is a lot smaller than what was originally reported in those papers. And then on peptide structure, we actually have the surprising result that GCN is still within the standard deviation of the best results reported on the current leaderboard. So here, this task can certainly be solved as well as with message passing GNNs as well as existing graph transformers. Okay, so moving on to the vision data sets, we have another confounding factor potentially influencing existing results concerning the normalization of features. So these data sets, well, they're model images as superpixel graphs. They have these node level features, which are basically 14-dimensional feature vectors for each vertex, where the first 12 dimensions encode statistics about colors, and the last two encode the position of the superpixel in absolute image space. And what we realize is that these last two dimensions are not normalized, as you can see in this heat map visualization of the matrix, but rather they were passed in the original LRGP results, they were passed into the neural network in their absolute values, while the remaining entries of this matrix were normalized. So clearly here the scaling between these channels is incomparable and may be a problem for may cause problems when learning on these inputs. What we would much rather want and what we use in our fully tuned results is a normalized version of this data set where we fitted normalization constants on each channel, on the training split of the data set, normalizing the ranges of each channel. Yes, so this is independently from hyperparameters, something that skews all reported results on the vision data sets needlessly. So here's a ablation study on exactly this effect, where again the blue bars represent the original results reported in the literature. The orange bars represent identical models trained in the same way, but now with normalized features. And we see significant improvements for all methods. Especially the simple GNNs make a massive jump towards better results when using these normalized features, but also the more complicated GNNs such as gated GCN as well as GPS improve a lot by using properly normalized input features. Finally, green is again the fully tuned version where yet again everything improves. Indicating that it's not just the GNN baselines that are undertuned here, but even the graph transformer itself. So if we now look at the tabular version again, we do see that we do see these improvements highlighted here. Note that the F1 score of Giant actually more than doubled by normalizing and tuning again. So clearly here the reported numbers are needlessly pessimistic. So I'd like to discuss this more, but I think I'll actually run short on time. So let me move towards the final data set, PCQM contact. As I said before, this is a link prediction task evaluated with a mean reciprocal rank as its evaluation metric, where we basically have to score pairs of vertices, and the aim is to score true pairs higher than false pairs. And of course, an important question here is how we handle false negatives. So a given head, it may have multiple true tails, and usually we would want to remove those and not use them as negatives when evaluating a positive tuple HT. And indeed, the LRGB paper does specify filtering out those false negatives before computing the MRR metric. But unfortunately, the provided code doesn't do that. So it actually computes the raw MRR with with false negatives present. In addition, the decoder they use is based on a symmetric dot product that strongly favors self-loops, although these are actually always negatives. So this is another concern we have for evaluating this, the results on this data set. So in our ablation, we actually study 3 different stages of filtering, where we use, first of all, the unfiltered version, which is the same as originally used in the paper, which was used by the original code base. We add in filtering of false negatives, and then we have an extended filtering where we filter false negatives, as well as self-loops. And what we see is this. In A, we have the original results for the 4 architectures. In B, we report our results using the same unfiltered MRR metric. And here we see after tuning, the reported performance margin of GPS actually disappeared. When we do filter negatives, everything shifts upwards, which is expected because now we are taking out, we are removing false negatives from the computation of the MRR metric. But the ranking of the architectures is not affected. And then finally, we have our extended filtering where we also remove self-loops. And here everything shifts up massively because these are always scored fairly highly, although they're always negatives. So here we have a massive uptick in the value of the MRR. Interestingly enough, here now we actually have a ranking again where GPS outperforms the GNN slightly, although B, C, and D are all based on the exact same prediction scores. So these nuanced differences in how we define and sample our negative values when we compute these linked prediction metrics can have a huge impact on even the actual ranking of methods we're comparing. So it must be done with great care and considered carefully how to do this. Okay, so maybe let me very quickly conclude here. Maybe with some general conclusions on LRGB. First of all, when you use any data set, but of course LRGB as well, hyperparameter tuning is absolutely important, especially when providing baseline numbers that are meant to be cited in follow-up research. So is feature normalization and other tricks of the trade, of course. One general conclusion we do seem to be able to draw from our results is that the peptides data set have some sort of strong nonlinear dependence on global graph statistics. So deep predictive heads should always be considered when working on them. Use the mean reciprocal rank metric with great care, especially with respect to how you define your negative samples. And one suggestion we have for the future is maybe we should switch to asymmetric prediction heads that do not favor self-loops on the PCQM contact data set. I have 2 more slides with conclusions, but I think I'm running out of time. So I can give you the very brief version of each. Basically, being more general than LRGB, but general concerns about evaluating graph transformers overall is that our data sets may be a little bit too small since they mostly have tens of thousands to hundreds of thousands of graphs, whereas transformers are known to perform best on massive scales of data sets. And it's not clear whether or not the commonly used graph benchmark data sets have sufficient scale to highlight those advantages. So one crucial thing in future work to get a full picture of the current zoo of architectures is to evaluate on much bigger data sets. And a very cool recent development I wanted to point to here to conclude with is Graphium, which was suggested very recently as a set of very large graph data sets specifically for pre-training, the largest of which actually has 80 million graphs, which is much, much bigger than anything we've seen before. And I really look forward to experiments on this. Yes, I have one more general slide with more generic conclusions as to be careful when working with benchmarks and baselines. But I think I'll leave it here if there's questions, because I think I am out of time.
Yeah, very nice. Thank you for this summary and this investigation into our large graph, or I don't know the exact name, into our long-range graph benchmark. And yeah, I think the Graphium library that you pointed out here, this is actually from the same folks that also made this large graph benchmark. So nice that we're discovering what the data sets are like on the one hand, and then we're having access and nice resources for these data sets on the other hand. And yeah, so one question that we have left in the chat is, it seems that unified engineering frameworks are crucial, or this, yeah, your unified engineering framework. Do you have any code available for your work and for how you fine tune and how you tweak your parameters?
Yes, I mean, first of all, we do have our code available. It's linked in the paper.
Yep.
Although actually the hyperparameter tuning is just a basic grid search we effectively did by hand, because the hyperparameter searches are basically are small enough to do this. So it's basically just a long list of Slurm jobs. But while we did this, we did realize that it would probably been a lot easier to use some sort of automated hyperparameter tuning library, say Optuna, or the sweeps available in weights and biases. So if I would do this again, we would use those. We actually did this particular sweep by hand, just by generating many Slurm jobs.
Yeah, but all the code is in the paper. So Francis Sun, if you want to check it out, there's nothing stopping you. And Chaitanya, any question from your side?
Yeah, thanks for the great talk and, really rigorous work. I think it's much needed, this sort of work in the community. I wonder if you had any reflections on the long-rangedness of these benchmarks, or, what sort of tasks do you think require long-range interactions?
Well, that's a great question. First of all, I think the long-rangedness of these tasks, it's somewhat inconclusive. It could be that they just don't depend more on long-range interaction than other tasks, and that's why we could observe these gaps closing. It may also be that there's simply work left to be done with graph transformers and really getting them to learn to exploit what they should, in theory, be better at. So maybe these data sets do actually have a dependence on LRGB, on long-range interactions, but it's not really been exploited as well as it can be. It's unclear. We have no definitive answer on this. I certainly don't discourage the usage of these data sets. I think they're great data sets. They just, based on what we know now, shouldn't be used as a definitive measure of long-range interactions or not. Now, as the second part of your questions, which tasks do depend on LRI? There's certainly, I think, one we can be certain of from natural language processing, right? Basically, the whole point of transformers in NLP is that they switch from the line graph that the recurrent neural networks of the olden days worked on to a fully connected graph. And there it really was this bottleneck created by this very sparse line graph that really limited performance. So this is a very clear-cut example of long-range interactions being of a true benefit. It's just that this task is not, it doesn't need to be modeled as a graph to be solved with transformers. So I guess that's that's somewhat limiting. We could probably still use it maybe to construct graph learning benchmark data sets, but that's a somewhat academic exercise. But certainly these tasks exist, I would say, just based on that.
So then, like, based on conducting this benchmark, what do you think are promising directions? Like, what are your recommendations for future work in long-range interaction modeling for graphs and also benchmarking?
Well, I certainly think the most important direction in benchmarking are the bigger data sets. Unless we have those, we will not know really where the transformers stand. Simply because almost regardless of graph characteristics, I think our data sets are mostly too small. So unless we resolve this issue, I think the specifics of the graphs, if they depend on LRI or not, are almost secondary to just the sheer scale of the data. So I think things like Graphium are exactly the right future work, and I really look forward to what will happen then.
Great. Yeah, thanks for all the responses.
Yeah, a big thanks from my side as well. And I think with that, we can say a very last summary here of the day. And first, of course, I want to thank you again, Jan, for the nice presentation and for letting us, not only for the presentation, for this rigorous work, this service to the community and looking into this in detail for real. And then with that, we're finishing our oral sessions. And with finishing our oral sessions, I also want to say to all our other friends of the Sun here, I hope you enjoyed our first day of the LOC conference, and we're starting again tomorrow, and we hope to see you there again. So, friends of the Sun, see you tomorrow. Chaitanya, do you think we should throw up the schedule a little bit for a while here while people log out?
You could. I think.
Yeah, I mean, people go to the website. You know.
What's the Friends of the Sun thing? Like, is it a German greeting or something translated to English, or?
It's sort of a German thing translated to English, but it doesn't really have a meaning. I should maybe stop it because people find it weird. It's just a habit now.
It's fun, but yeah, I think no one knows what it is, right? So it's like
everyone should be a friend of the sun. Who doesn't like the sun? So
yeah, I know. I think it's important to get some sun.
Okay, well then see you tomorrow as well. And Michael, Jan, Chao, Ali, and friends, almost friends of the sun again. See you all tomorrow as well.
Bye-bye.
Have a nice day. Bye.